All right, good morning, everyone. Thank you for joining us. Thank you for sticking around, especially to the last day of this conference. It's been quite a lot of presentations and quite a lot to get through, so we really appreciate your patience and willingness to stick it out. And we've only got 2 sessions left. This is our session HA1. Just friendly reminder for anybody who's forgot, when the bathrooms are down that way. Please refrain from speaking about anything that relates to pending matters before the commission. And with that, I think we can go ahead and get started and welcome our first presenter for this session. Our presenter will be Will Frazier from Encore. Will is going to present on a day-ahead contingency planning solution that captures the physics of electric and gas networks. Will, thank you.
So speaking of software efficiency.
Thanks for bearing with us.
So yeah, my name is Will Frazier. I lead the data team at NCORD. NCORD's a software company. It's short for Energy Coordination. And first, I want to thank FERC. This has been a fantastic conference. There have been very minimal technical issues up to this point. So I want to applaud them for that. It's my first time attending. I would attend again. I would recommend others. So I've met a lot of great people, seen a lot of great presentations. And before I jump in, I just want to share my own personal opinion. And the name of this conference is the increasing real-time and increasing the efficiency of real-time and market planning efficiency through improved software. And it's my opinion that where we're going to make the greatest gains in improving efficiency, unfortunately, is not going to be the sexy stuff. I know that there have been a lot of fantastic presentations and ideas, and I'm excited to see the impact that those make. But I think that where we're going to see the most gains is simply by using efficient software development practices. And that goes from the software vendors all the way down to interns writing Python scripts to automate processes, because that in and of itself is software. So I would recommend we all take those software development practices a little more seriously and maybe look to other fields like data science, data engineering that have gone through a lot of these they've learned these same lessons and they've developed some best practices to manage large amounts of data moving through complex models. So I'll step off that soapbox and on to another one here and get to the topic of my presentation, which is capturing the physics of electric and gas networks in planning. And the purpose of this is primarily to discuss the 2 competing objectives that are most important in power systems modeling, and that's reliability and economics. And with current standard approaches, we can model system reliability with nonlinear physical simulations, and we can model economics primarily with linear mixed integer optimization problems. However, these linearized approximations may no longer hold, or at least may become more difficult to justify because of the greater diversity in power system dispatch conditions that we're seeing. So as more wind and solar and storage are deployed, it's difficult to know with certainty whether these approximations will hold. And a strong argument can be made that it's the flexibility of natural gas that has allowed for the rapid deployment of wind, solar, and storage so far. So I'll take the next slide, please. So our software, SAINT, which stands for the Scenario Analysis Interface, allows for what I would consider true integrated energy network planning. And I've defined what I mean by integrated energy network planning on the slide here. It's the ability to coordinate between different planning processes and across different domains to balance these competing objectives of reliability and economics. So I think integrated planning should include planning across different networks, and mainly I mean power and gas when I say that. And it should include different mathematical domains, and today I'll talk a little bit about the seam between AC power flow and production cost modeling. And doing this allows us to explicitly plan for both economics and reliability. I'll take the next slide. Next slide, please. Okay, so I'm going to focus on the seams between these planning processes. And today, specifically, I'm going to focus on electricity generation and gas delivery and electricity generation and transmission. And what I'm going to do is I'm going to walk through two examples using our software to manage the data exchange through these planning seams so we can efficiently plan for both reliability and economics. So we'll go to the next slide. I'm going to start with an example of coordinating across electric generation and gas delivery. Next slide, please. So this is a screenshot of two energy networks loaded into our software. This is a electric system in red and a gas system in green based on the Belgian power system. This is a test system of ours that goes all the way back to our CTO's PhD days when he was doing combined electric and gas simulations for his PhD. So the electric data we have here includes all of the normal objects and relationships you would have in a model in PSSE or PSLF. In addition to that, the time series data and additional properties you would need to model the economics in a software like Plexos, PSO, Prescient. There are many other examples. Plus coordinate system data so we can overlay that onto a map and see that along with the gas system and the connections between the two. So for the gas data, we have all the facilities and pipelines we would need for a hydraulic gas model and the object properties and scenario data therein to perform that. So I'll take the next slide. So this is a very simplified schematic of the example I'm going to do here. So we're just going to do a one-way iteration here, where first we're going to dispatch the electric power system without any constraints on the gas fuel supply for gas-fired generators. And then we have those fuel supplies for these gas-fired generators linked with gas demands in the gas model, so we can run our hydraulic gas model referring directly to the solution of the production cost model as the gas demands in that model that correspond to the gas-fired generators in the electric model. And when we do that, we can identify any gas fuel delivery constraints, and then we can come back and run another iteration of our production cost model where we explicitly have the gas fuel supply constraints identified in the gas model included in our power system economic model. So next slide, please. So on the right here, we have a simple stack dispatch plot of the first electric power system optimization. So we can see lots of solar in the middle of the day, storage doing some load shifting and handling the peaks in the morning and the evening, and notably a large ramp down of gas-fired generation. That's that pink band in the middle to allow for this amount of solar to go onto the system. And on the left is the total fuel consumption curve from a particular gas-fired generator in the system, which happens to be operating at its maximum capacity in the morning and evening and ramping down to its minimum capacity to allow for solar power to make it onto the grid and into storage in the middle of the day. Next slide, please. So these are a couple plots from our gas dynamic simulation. So on the top left there, the orange line corresponds to the pressure at the gas offtake point for that particular generator we were looking at in the previous slide. And the red dash line is the minimum offtake pressure that must be met in order for this generator to consume fuel from the gas network. And we see a little bit after noon there, we actually do hit the minimum pressure, and that persists for the rest of the day. So we're limited at that point in the amount of gas this generator can physically consume from the gas network. And that plot on the bottom there shows the fuel consumption. This is actually the fuel supply. The red dashed line shows the fuel demand from the generator, and filled in blue is the amount of fuel that the gas system is able to deliver to this generator. Next slide, please. So on the left again, this was our dispatch with the PCM only, and we ran our PCM again, and now there's a constraint on the fuel consumption for this generator that's pointing directly to the solution from our hydraulic gas model. And we see the amount of generation from this generator significantly dip once we experience that supply constraint in our gas network. So much so to the point where the amount of fuel that could be delivered to this generator is less than what it would need to operate at its minimum capacity. So this generator actually completely turns off for a few hours in the evening when the system would need it most. And we see its generation start to ramp back up later on as the gas system becomes more stable. Next slide, please. So I've highlighted that the little dash circle in red, we can see the bumpy ride that we have as we're experiencing some gas fuel supply constraints on the back half of the day here. This is our production cost model dispatch, the stack dispatch plot for the whole system, considering the fuel supply constraints from the gas model. And we can see this bumpy ride costs us to the tune of about €250,000. And this has both economic impact and reliability impact that we can capture by using this process of iterating between the two. I'll take the next slide. So I'm going to walk through one more quick example. Here I'm going to talk about coordinating across electric generation and transmission. So next slide, please. So again, starting with the data, what we're looking at now is the IEEE 39 bus system. We've overlaid this onto New England. This system is supposed to loosely represent New England at some point in the last 20 or 30 years. And we've layered onto that the additional time series demand and generator properties that are needed for production cost modeling, and we validated the AC power flow against results from other tools. So next slide. So again, we're going to do a simple one-way iteration. And there's a lot that's not shown here. Mainly the difference in power losses between the different models. So this first step of taking the production cost modeling results and using those as inputs to an AC power flow model, there's a lot more that's happening there. We followed a paper that was published a couple of years ago from EPRI that established what they recommended as best practices for linking production cost models with AC power flow systems. If you have specific questions about that, I'd be happy to answer those, or at least just point you to the paper that we used to guide the workflow that we use to converge the simulations as best we could. And then we're going to, once we have our AC power flow simulations, we can identify if there are any reliability issues, and then potentially redispatch our system with those additional constraints or additional objects or whatever is deemed necessary to mitigate any issues that we see within our production cost model. Next slide, please. So we ran a full year for our production cost model. So rather than looking at the entire year, we're going to zoom in to just the week of peak demand. So I have that highlighted so we can see the dispatch that we have for the week of peak demand. And what we're going to do is we're going to use all of those generator dispatch levels as power set points for our AC power flow model. And we're going to run through a full time series of this week to look at the load flow analysis in the system at each time point during the week here. So next slide. And what we see here, and this is actually kind of fun because we started with the 39 bus system and we thought we were going to have to artificially engineer something interesting to happen. But what we actually found was that these two nodes here at the edge of the system, so these are represented by Augusta, Maine and Portland, Maine, we found there was actually over voltage conditions at those nodes during hours of low demand. So those that plot on the top there, the green and yellow lines correspond to the voltage magnitude in terms of per unit at those nodes, and the red line is the maximum acceptable. And we see during some periods of low demand, which demand is the oscillating gray curve in that plot, we have some over voltage at those particular nodes. So what we see, the plot on the bottom there, the purple line shows the reactive power consumption from the largest fuel generator up in that region. That's that Westbrook generator that's labeled in gray in the map. So this generator is providing a lot of reactive power support by consuming reactive power to keep the voltage within its accepted bounds. And what we see is when this generator is turned off due to economic reasons from the production cost model, the voltage spikes at these nodes at the edge of the system, and we see some overvoltage violations. So next slide, please. One way to mitigate this would be just to add reactive power support at the edge of the network. So here we added an inductive shunt to the Augusta main node, and we switch this shunt on whenever the generator is off. And as we can see in the top plot there, the voltage magnitudes for those two nodes are now within their accepted bounds for the entire duration of the simulation. Excuse me. We also went back and redispatched the power system for the entire year, and we modified the outage profile of that specific generator, Westbrook up there, such that at least one unit was available at all times, and we made that generator must run in our production cost model. And we were also able to mitigate the overvoltage conditions at those nodes. And we found that there was an increase in the operational cost of the system of about $15 million in the year to keep those generators online to provide reactive power support throughout the entire year. So there would be a cost-benefit analysis of what would be the most efficient solution in terms of a physical network solution and adding some reactive power support at that edge of the network, or an operational solution, just changing the way that we're operating the generator near those nodes to make sure that we have the reactive power support available during all hours. Next slide, please. Okay, so in conclusion, again, the purpose of this presentation is to discuss the competing objectives of reliability and economics. Next slide. And so what we did is we modeled the physics of both electric and gas networks, and we considered both economics and reliability by modeling both the unit commitment economic dispatch and the performing physical simulations to validate explicitly that those dispatch conditions are reliable and feasible. And we did this using our software, which manages the data exchange between those various modules for us in an efficient way. on a single platform with a single source of truth, unified data structure. So I think next slide is just questions. I'll stop there. Thank you for your attention and for staying for the last day.
Thank you, Will. Check 1, 2, check. Thank you, Will. Any questions in person?
Yeah, they're very interesting talk. So can you go back to the slides where you have the curve?
I can't control the slides.
Anyways,
You know the number?
Yeah, I don't remember the number,
The one
but
with the,
keep going back.
over voltage?
Oh,
Yeah.
no, it's keep going back. Keep going. Yeah.
Okay, there.
Sorry.
The gas model.
So what is reason for the blue, like after the long time, and there's a deep drop on the blue part?
So we ran this gas simulation with a gas fuel supply constraint during the middle of the day. And although there is enough gas supply available, the system conditions are such that you can't move the gas through the system. So unlike electricity, the amount of gas you can move through a gas system depends on how that system's been operated in the recent past. And you can imagine that if you have nice laminar flow, that's when you can get the most amount of gas through the system. But when you're starting and stopping, those waves move through the system at the speed of sound as opposed to the speed of light is the speed at which signals move through an electricity system. So it's those pressure conditions in the gas network that are limiting the fuel supply.
The gas network, they also have storage. They have a turbine to increase the pressure, right? So the gas networks, it should be prepared for consumption from certain points, pressure decrease, and they have the equipment, right? So my question actually is that how important is this coupling between gas and electricity? I mean, from your perspective, you observed from the real world, like how serious is the concern it is?
From my perspective, I think it's a legitimate and serious concern. And I know that up to this point, these have largely been managed. There are certain extreme weather scenarios where there have been some issues with gas supply that have affected the electricity sector substantially. And as the dispatch conditions in the power system become broader and we see more and more variability, I think it will become more important to coordinate between the two sectors to know when we're planning for electricity reliability, we need to plan for the reliability of fuel supply from the gas system.
Okay. The last question, are you aware of this energy transient, natural gas transient?
Yeah, I'm aware of it. Yes. Yeah, I'm aware, and I'm curious to learn a little more. And gas modeling is not my personal expertise. My background is in power system economics. But yeah, I'm aware there are other possible ways to coordinate.
Yujie from ISO New England. I have two questions. One is when you did the simulation for a whole year, you said the cost to run the Westbrook unit is additional $12 million. Other than that, have you tried to quantify the whole system's economic savings by considering the gas constraint for the electrical system? or quantify the cost when we don't consider the gas limitation. And then maybe we could run into load shed events or.
I did not explicitly consider cost savings in terms of avoiding shedded load. But that's a really good point and something we should probably look into.
Another thought is, I think this tool probably will be very useful for generators to optimize their strategy, because they need to nominate their gas consumption from the gas network before the market day. So I think that's another direction to consider.
Thank you. Appreciate that.
Do we have any other questions?
Hey, Adam Christensen from GAMS. I just had a quick question. If you had any lessons learned, hard-won lessons on data scalability, if you've had problems with kind of going to really huge networks, or if you've been able to do that successfully, and then kind of what tools you've been using, and just kind of curious to know a little bit more about, yeah, really going big on the gas network and electricity networks. So.
Yeah, of course. So in terms of increasing efficiency, I think the aim of the presentation was to show the value of efficient data exchange, but you still don't get around needing to build those models within the software to begin with. And we've been trying to look to other industries, specifically the data science and data engineering community, to help us adopt some best practices in terms of data validation and being consistent and establishing good practices on getting data into the tool, which really is often a bottleneck and one that we're trying to take seriously. So we're doing our best to develop tools to allow people to import data from other software formats. Does that answer your question?
Yeah.
Okay.
All right. Anybody else? Anybody online? Okay. Thank you.
Thank you.
All right, thank you, Will. We're going to try to hear Eric Allen again from Smart Grids. Eric, are you available in the Zoom?
Can you hear me now?
Yeah, you sound good. Are you able to are you able to see slides or see the Zoom webinar?
I see you speaking at a podium.
Okay. Rob, can you try and get his slides up, please, and we'll see what happens.
I see my slides.
Okay, great.
Did we want to start? Did we want to start from the beginning again, or pick up from here?
Wherever you'd like. If the beginning's good, we can start.
Okay. Thank you, everyone, especially the staff, for your patience with these computer issues associated with a certain computer operating system. Without further ado, again, my name is Eric Allen. I am the Director of Engineering for Smart Grids, and I'm here to talk about software for system model validation. Next, please. I'm going to start by giving an overview of what system model validation is, then talk about extended AC power flow, what it is, how it works, how we can use extended AC optimal power flow for system model validation, and then conclude with what we like to call a real-world example from the industry. Next. So steady state system model validation is the process of verifying that the power flow models which are used for planning and operating studies accurately reflect how the system actually behaves. This procedure was recommended as a result of the analysis of the August 14th, 2003 blackout. Through a series of steps, that recommendation eventually became a NERC standard, MOD 033, which requires the periodic performance of this procedure every 2 years, as I recall. It is also an essential first step to do any kind of an event analysis. The starting case requires the same procedure be performed. And what it basically takes place here is taking the power flow case, which is used for studies, and adjusting individual components in that case to represent a particular point in time, loads being the major adjustment. This sounds simple, but it is not nearly so simple because the topology of the cases used for these offline studies is very different from the topology of the real-time operating models, such as state estimators. Next, please. So as I stated, we're going to be creating a power flow case that represents a specific point in time. We'll be using system measurement data and optimizing the load profile to minimize the error between what is in the power flow case and the measured values of system voltages and flows at that time. This procedure is used to benchmark power flow cases per the NERC standard and is also a starting point for event analysis. Next, please. Historically, this process has been very cumbersome and time-consuming because, as I noted, the components in these power flow cases, particularly the loads, do not directly correspond to elements in the real-time state estimator models or in general the real-time operating systems. So the power flow case has always had to be adjusted manually via a trial and error process, and as a result, weeks or even months have been spent just to build one single case for this procedure. However, we note that this is a process that can be cast as an optimization problem. We're simply trying to find the values of loads and other components which best match the available measurements. So by applying software, we can do in one single run what requires much trial and error using the conventional procedures. And we go from solving this problem in weeks or even months down to solving in a few minutes. And furthermore, the results of the optimization, in particular residuals between quantities in the case and measurements, can point to where your data problems are located. Next, please. So the optimization that we're using is something known as extended optimal power flow. This is our core software. This determines the optimal resource allocation or optimal dispatch across a static snapshot of a bulk power grid. It can be applied to planning, operations planning, and real-time operations. There are many key features here. Many optimization objectives are available. We'll go over on the next slide. Voltages can be optimized and dispatched. Sorry, go back. Voltages can be optimized. The procedure is able to both explain and eliminate infeasibility. Bottlenecks in rank order can be identified, and the software has substantial data error checking in it. Next, please. The optimizations that are available in our extended optimal power flow include an optimal real power flow, which I think most everyone here is familiar with, which is minimizing a generation cost. But optimization can also be done with optimal reactive power flow and an optimal apparent power flow, where we assign a cost to reactive or apparent power for each generator instead of real power. Branch flow management is available, in which flows beyond certain flow limits or flow guidelines are minimized. Load distribution management, which can be used to maximize the amount of load that can be served for a given system condition, and also voltage profile management to minimize any extreme voltages beyond desired boundaries. Software is also all physical limits are observed. Any thermal voltage limits, power generation limits. The optimization engine can be accessed either through a graphical user interface, as shown on the top right, or scripting code such as C++ or Python can be used to access the optimization engine and operate the program that way. Next, please. So what we do with extended optimal power flow is to minimize the desired objective function. The specific decision variables which are available are identified in here in red. Either generator voltage set points or a generator reactive output could be chosen as a decision variable. The real power output of generators, the transformer taps and angles, switch shunt admittances, DC line power flow settings, and adjustable loads, the amount of load at each bus. And all of this still observes the real and reactive power balance at all of the nodes. Next, please. So for system model validation, the optimization objective that we wish to solve is shown by this equation here. It is a weighted least square sum of the differences between the real power flows in the case and their measurements, and the reactive power flows in the case and their measurements, and the voltages in the case and their measurements. As I noted, the principal decision variable is the load scaling factor. The case is assembled with a sort of a certain assumption or modeling of the load. Each of those loads can then be scaled to better match what was actually the load at a particular point in time. So that's what I mean by load scaling. Any transformer tap ratios, phase shifter angles, and shunt admittances that were not known or readily available can also be adjusted as part of this optimization. And any P and Q output for generators which may not be known in the data, typically for some small units, they may not be individually known. Those values can be adjusted as well. And of course, the power flow balance relations must be maintained. Next, please. So the problem is, given an offline study case, we presume that we have the correct status of all of the equipment, any lines that are out of service, et cetera, any generators out of service. We have voltage measurements for some buses. We have most of the generators are known. As I say, some of the small ones may be aggregated, or not explicitly modeled, but most larger generators are known. We know some of the line flows, real and reactive. We may know some of the taps and shunt susceptances as well. Next, please. So we adjust all of these decision variables to find the set which best matches the available measurements, and best match is defined by that objective that I showed earlier. So the principal changes are the loads. We note that the real and reactive power of loads is scaled separately. Find the best match. The load power factor assumption in the original case may not really be correct. And loads could be scaled individually, or they could be grouped by area or zone, or any other defined grouping, and a single scale factor assigned for that group. And the decision as to whether to use groups or not, or what kind of groups to use, depends really on the granularity of the system measurements that you have available. If you have all of the lines between each of the individual loads in the case, then it makes sense to scale each load individually. But if the loads are at a lower voltage level where you lack a lot of data, then using a grouping would make a lot more sense. As noted, small P and Q for small generators would also be a decision variable, and transformers and shunts if not known. Next, please. Sometime a little while ago, while the process of converting the system model validation recommendation into a standard was going on, a group called the NERC Model Validation Task Force put down a procedure to perform validation of power flow and dynamics cases. And here's an outline of the procedures that they came up with. The first step is to select the starting power flow case, the case to be validated. So it might be a summer peak case, is typically the most interest for a lot of places. Then step 2 is to collect the recorded power system data for a selected time. And to validate a summer peak case, you would find some time during your summer when you had essentially peak load conditions. Yesterday might be a good example of that. Next, please. Then that data gets transferred into the optimization problem. The generators, real and reactive power, if the generators are known, those data are generally assumed to be very accurate. So the decision variables are essentially fixed for those particular generators, which is fixing the limits so that they don't change. The status is also taken directly from the data. Bus voltages and line flows for the transmission are applied as objectives in the optimization problem. In our parlance, VL, VH, FL, FH are flow and voltage objectives. The line status, of course, gets transferred directly, and if any shunts or taps are known, those are essentially fixed at those values. Next, please. So then the optimization is run to complete step 4 of this procedure. And as I have said before, real and reactive load adjustments are the main decision variable, but also small generators typically is transformer taps and shunts. Next, please. So what do we get out of doing all of this? A major motivation is to compare the load power factor that results from the optimization with the assumed load power factor in the starting case. Load power factor modeling was a major motivation for the whole recommendation. So this optimization will tell you whether you're using a valid assumption for load power factor. Also, large residuals in the voltages, and these tend to be major outliers. You might have one flow that's off by 100 megawatts where most others are within 10 or less. If you see something like that, it indicates that possibly you have a device status that is incorrect. And another very common issue is having sign errors somewhere in the measurement data. Also, it may indicate that the parameter for a component is wrong. For example, maybe the line reactance somewhere is wrong. Whereas if you get small and generally normally distributed residuals, that indicates that the case is ready to use for planning studies and event analysis. And these power flow cases are typically the ones that are required to run a dynamic study because they are the cases to which the dynamics data is matched. Next, please. So the example we have came from ISO New England. The full case has 80,000 buses. Of these, 4,600 represent New England itself, and 6,200 represent the areas adjacent to New England. ISO New England gave us some state estimator output as opposed to direct measurements, but they can be used just the same for this procedure. We chose to group loads by zone within New England and by area for each of the areas adjacent to but outside of New England. And as noted, P and Q for each load group is scaled separately. We also note that ISO New England had already done work to align the real power flows, but had not done the reactive power flows or voltages. And that was actually one of the reasons of interest for using our software here in this procedure. Next, please. So here are what the results of the optimization look like. The top row shows you what the status of the case before running the optimization, and the bottom row is after running the optimization. The blue circles indicate a particular quantity in the case, either a particular line or a particular bus voltage for the right column. And the red squares indicate what that same line or bus voltage was in the state estimator data. So we're trying to get the blue circles to land on top of the red squares. The leftmost column is real line power flows, and you can see, as you can see, it was already pretty closely matched to start with, but our optimization still made it even better. You can see a more dramatic change in the middle column, which is reactive line power flows. You can see that when the optimization is run, we get a much better fit to the estimator data, and certainly you see a very dramatic improvement here for the voltages on the rightmost column. Next, please. Another way of looking at this data is through histograms, and that's what's shown here. And you can see that the histograms get narrower and taller for each of the different categories, meaning that the deviations between case and state estimator data get smaller. So and it's especially notable for the right two quantities, which are reactive power flow, reactive line flow, and bus voltages. Next, please. So in conclusion, what we've demonstrated here is that system model validation can be performed using an optimization as opposed to a tedious trial and error process. In our case, we have a slightly improved real power line flow match, and that, of course, reflects the fact the starting case has already been worked on. But we saw much more significant improvements in both the reactive line flows and the voltages relative to the state estimator data. And as noted, instead of spending weeks to do this, this only required a few minutes. This particular optimization problem with 10,000 buses solved in about 5 minutes or so, if that. So next. So thank you very much for your patience and your attention, and I'm now ready for questions.
Thanks so much, Eric, and thanks for bearing with us. Do we have any questions from our in-person audience? Two at the same time. Okay. Please introduce yourself.
Yeah, my name is Felix from Great Insights. It's not a question, more like a comments. I will really excited to see if you can apply your software on the dynamic model tuning or parameter observation, because in that domain, it requires a lot of expertise and a lot of time to tune, especially renewable IBR model to match the field measurement. So I believe, observation can solve everything, but if you can, try that, or have you already tried that on the dynamic model, that would be great.
Thank you. I mean, the current formulation here is for a power flow case, but that power flow case is often needed to start a dynamic simulation.
Thanks. We'll mix it up and take a question from the virtual audience for our next in-person question.
Dick O'Neill, I'm going to allow you to unmute. All right, go ahead.
My question was, what does it mean to optimize voltage or reactive power?
Should we go back to that slide? Do you have it to be more specific?
The specific question is what, I mean, I understand an objective function that gets you nearer to a set point. Is that what you're optimizing? I mean, you said optimize voltage or optimize reactive power. I don't know what that means.
Well, there's the OPF objective is to find the real power output, which typically is a minimum cost. The reactive power, the OQF function, optimized reactive power, is a case of assigning linear and quadratic cost factors to the reactive output of each generator, and then finding the dispatch at which that total cost based on Q of each generator is minimized. Does that make sense to you?
Oh, okay. I didn't see that. So yeah, I understand what you're saying now. And what about voltage? I mean, the equation, the objective function was to minimize the distance between the measurement and the solution, right?
For system model validation, yes.
Okay.
The earlier slide showed a more broad range of objectives that are available.
Okay.
But then that later slide is specifically system model validation.
Yeah, and so the question then is, what does it mean to optimize voltage in any of those formulations?
Basically, it means that voltage is a decision variable. So the voltage set points that produce, say, the lowest real power cost or lowest reactive power cost are the ones that are selected. I mean, allowing voltage set points to be a decision variable.
Okay, no, that clarifies it. Thanks.
Okay, thank you.
Thank you. We'll take another in-person question.
Nicolas Aumont from Artelis. Is the optimization problem continuous, or do you also have integer constraints? And the second question is, would you think that detecting topology errors on the status of line would be needed or would be an improvement?
I'm not sure if you asked if the first problem is continuous. I don't know that I have a proof that it is, but I believe it is.
Well, for example, for shunts, they are either on or off, so this is not continuous. So how do you handle it? And yeah, and same thing for the line status. They are either on or off. So it's if you want to optimize to find the best status, it's not continuous.
That would be future research. As currently formulated, we take the line status as given. I would note, though, that if you have a line status wrong, it will stick out very much in the residuals. The largest residuals are right around where the line status is wrong, and that points to a need to address where to fix the problem.
Yeah, but somehow, yeah, you may want to correct it as you correct the measurements to find the best measurement. It's going to require manual intervention. It's going to take time and be costly. Whereas if it could be handled directly by the model.
Thank you. Yes, that's future work.
Thank you. Any more in-person questions? Any more virtual questions? All right, let's give a round of applause for okay. Thank you. Our next speaker will be Iven Guzel. Iven is from University of Illinois at Urbana-Champaign. Iven will present on power system state estimation by phase synchronization and eigenvectors. Iven, please.
Hi, good morning, everyone. I am Iven Guzel, and I am from the IUC. So I'm gonna present our recent research, and this research is co-authored with my PhD advisor, Richard Jung. Next slide, please. So power system state estimation is essentially the eyes and ears of the system because it allows us to achieve and maintain situational awareness in large grids. And in this problem, we are trying to estimate complex bus voltage phasors from noisy and possibly incomplete voltage magnitude and power measurements that are collected from various points from these large grids. And to achieve this, we are solving a nonlinear least squares problem using an iterative algorithm such as Gauss-Newton. But the problem with this is that this problem is non-convex, and also this is the issue that our work is tackling, this non-convexity. So if I use a greedy algorithm like Gauss-Newton, it might get stuck at a bad local min, and when it does, this bad local min might not look like the true system state, and it might cause some serious mistakes in the grid operation. Next slide, please. Oh, okay, so where were we? Yeah, a non-convex function. So let's suppose that I suppose a bad initial point, then I greedily refine this initial guess. I am going to end up at the bad local min, right? And this bad local min can cause two issues. The first one is that the local min may be completely different than the globally optimal point that we are trying to compute, which means that this state estimation will not reflect the true system state. And the second one, I think it's there, but it is kind of less obvious, is that you can't tell a bad local min from the globally optimal one. I mean, in the one-dimensional case, I can just plot the function and see the rest of the curve. But say I have 1,000 dimensions, then how am I supposed to tell, right? So the way we are checking this thing in power systems is that we are keeping a human expert in the loop, and they look at the state estimation and decide whether it seems unlikely or not. And indeed, some of these bad local min doesn't even look like physically makes sense, right? And but this approach is still prone to error because we are now having an increasing variable and uncertain grid, and also we might like to encapsulate more automation in the grid as well. Then we're gonna need some algorithmic means to verify the goodness of a solution as well. So this brings me to the next slide, which is about certifying global. Next slide, which is about certifying global optimality of a solution. So there has been great progress on this line of research. And the idea is quite simple. So you take the non-convex function and find the convex relaxation in some way. And once I solve the convex relaxation, then it's gonna give me a provable lower bound on the cost of the global optimal solution of that non-convex function. And if the cost of my state estimation equals to this lower bound, then I'm gonna say that this solution is guaranteed to be globally optimal. And in practice, we don't need these values to match perfectly. If the gap between these dashed lines are quite small, then you can certify optimality with great confidence. For instance, if this ratio is 99%, then I'm going to say that this solution is at least 99% optimal. This idea seems great, right? And I am not just saying that because it is my PhD topic. But there's a problem. So if this gap is large, then your lower bound is going to be useless, and the current methods to find these lower bounds are giving either too loose lower bounds or they are too expensive to solve. For instance, SDP usually gives really tight lower bounds for power systems applications, but it is crazy expensive to solve an SDP problem. So to summarize, this idea seems really great, but I mean, it can help us to augment the human expert in the system, and also it can allow us to facilitate more automation in the system. But right now, the computational cost makes it completely out of the question. Next slide, please. And so we talked about bad local min and how it could look really different than the global one, right? So I have a really simple system here, 3 bus, very small, very simple. And I measure the PQ injections at each bus, so the system is observable. Moreover, I fixed the voltage magnitudes as well. So I eliminate the ambiguity between the high and low voltage solutions of the power equations completely. And despite all of this, I have two local minima. Moreover, the common initialization technique called the cold start, where I take my initial guess for the angles as 0, takes us to the bad local min. And I'm looking at this bad local min. It looks plausible. I mean, the angle differences are quite large, but they are still below 90 degrees. So, but if my operational point looked like this, my head would be on fire, and I would like to do something immediately. Alas, the bad local min looks completely different than the global min. I mean, the global min at the other corner of the figure right now. So, yeah, this is a problematic situation. And to finally, that red cross that you are seeing is the initialization method that we are proposing, and it gives almost a single shot estimation of the global optimal point. Moreover, this method will also let you certify the optimality as well. Next slide. So we are able to achieve these things because we make a fundamental connection between the phase synchronization problem. This problem is a well-studied problem in signal processing and inference. And in this problem, you try to estimate angles from noisy pairwise angle difference measurements. So the first contribution. Given the voltage magnitudes, we give an exactly equivalent formulation to the state estimation problem. And then if I take this, if I look at this phase synchronization problem, the special mathematical structure of it allows us to use a technique called spectral initialization. And some properties of this H matrix allows us to find exceptionally high quality initial guesses over the angles. And the third contribution is also due to this, thanks to this mathematical formulation, we are allowed to certify angles via computed lower bounds. And our experiments shows that we find really tight lower bounds for this instance of problem. And the fourth one, I mentioned you can find lower bounds using STP, but they are crazy expensive to solve. But we formulate these problems as sparse eigenvalue problems. And it is really fast. For instance, if for a 13K bus system, we solve these problems within time equivalent to 6 Gauss-Newton iterations. This is a little bit detailed, but one final word is that we inspired by the classic phase synchronization problem, but due to some differences in our formulation, mainly the chordal sparsity and positive definiteness of the H matrix, this method actually works better than the classic one. Next slide. So I want to skip the details on the reformulation and the certification of optimality to last. And if we have time, we can talk about it. But I want to go over the spectral initialization because I want to give you a sneak peek on how this phase synchronization formulation may allow us to how we can utilize this reformulation. So that's why we are bothering with this reformulation. So the first line is the regular problem, and with the indicated the part in red, I'm doing a relaxation. And so note that this relaxation is not a convex one due to the constraint in the second problem, but it is a relaxation because if you satisfy the constraints on the first line, then you can always satisfy the constraint on the below, but the reverse may not be true. So we have a larger search space, therefore it is a relaxation. Therefore it's going to give me a lower bound as well, but it's just a detail. So this is a nonlinear problem, but I don't have to solve it iteratively because due to a well-known theorem called the Cron-Fisher theorem, the answer to this, the solution to this problem will be the minimum eigenvalue times n, and also the corresponding eigenvector will minimize the problem as well. And then I'm gonna put the found x right back to the search space as a final step. And this relaxation works really well because this initialization works really well because if we have small noise, then we expect the value of that opt value to be really small. And also we have a positive definite matrix. So therefore that value will always be positive for the relaxed problem as well. So therefore, even if we put X right back to the source space, we have accurate initial guesses. Next slide. Okay, so I'm skipping to the experimental part because we think that it is more interesting. And we repeated these experiments for the whole cases and whole French, Polish, and RT cases that comes with the MetPower library. But I'm reporting the results corresponding to the largest one. Let me summarize what happens in this figure. So x-axis corresponds to the standard deviation of the power measurement error noise. And for each sigma noise value, I repeat, let's say 50 random trials, adding random noise to the power measurements. Then I solve the regular Gauss-Newton problem for the state estimation. And since I know the voltage magnitudes in this experiment, I just solve for the angles. And I took then, among those random trials, I record the angular error corresponding to each iterate, and I took the average and plotted. And what we are seeing is that spectral initialization gives exceptionally good initial guesses when we have accurate voltage magnitudes. And within one iteration, the Gauss-Newton algorithm converges. And I benchmarked the same thing with the cold start initialization on right, and you see that it takes 5 iterations to achieve that kind of accuracy. Next slide. And now in this experiment, I do the same procedure, except that right now I'm recording the average cost and the computed lower bound proposed by our method for each iterate. And for the dashed lines, they are for the lower bounds and the solid ones for the costs. And right now you see that within one iteration, we are able to certify the optimality of angles for given accurate voltage magnitudes if we start from cost spectral initialization. And on the right plot, we show that we are able to use our proposed certification method with other initialization algorithms as well, such as cold start, but it takes more iterations to achieve optimality and certify it. Next slide, please. Okay, so until this point, I said that we have accurate voltage magnitudes, but that's not reality in state estimation. We also measure the voltage magnitudes as well, right? So they are going to be noisy. So in this experiment, we also add noise to the voltage magnitude measurements as well. And that delta U values are level of noises, and they are in per unit. The top plot is for, also since we don't know the voltage magnitudes right now, if I'm using the Gauss-Newton algorithm, I'm solving for both my magnitudes and angles. And the top plot again records the angular error associated with each iterate. You can see that the first figure is for spectral initialization, and you can see that after 5 iterations, we have for moderate voltage magnitude noise, we achieve almost the same accuracy. And when we have high voltage magnitude error, you see that we actually achieve better results with spectral initialization. We actually estimate angles better because I think it's the reason is why the voltage magnitude error causes the Gauss-Newton algorithm to stagnate, and I think that causes this. And below, we see that once we have accurately enough voltage magnitude estimates, we are able to certify the optimality of angles using that as well after 5 Gauss-Newton iterations, except for really large voltage magnitude error. Okay, next slide, please. Okay, so let me describe this table again, because you see a lot of things right now. So the second column is for the number of buses in MetPower cases, and the third one is the number of measurements. And in this table, in the other columns, we are recording the computational cost of solving Gauss-Newton. And the final 2 columns are the average ratio between the initialization or the certification and time that it takes per Gauss Newton iteration. And I mentioned that the special structure of phase synchronization allows us to formulate the initialization and certification problems as sparse eigenvalue problems. And that allows us to solve the initialization and certification problems within time equivalent to 6 Gauss Newton iterations. And this timing is slightly better for the certification problem. Next slide, please. Okay, so to conclude my presentation, so in this work we present a novel and exactly equivalent reformulation for the angle estimation subproblem of state estimation as a phase synchronization problem. And this special structure of phase synchronization allows us to achieve a significantly faster method than other initialization and certification methods. And finally, a final word is that this achieving certification this fast is, I think, in our opinions, actually shows a proof of concept for certifiable estimates in power systems as well. I mean, sure, we started with the state estimation problem because state estimation problem is perhaps one of the easiest nonlinear problems in power system operations because you don't have any infeasibility issues. But the next step is applying this algorithm to optimal power flow. Thank you.
Thank you, Ivan. Do we have any questions from the in-person audience?
Oh, before I take the questions, also I have slides for the reformulation and certification. So if you have questions, I can answer them with the slides as well. Sorry, go ahead.
Nicolas Aumont from Artelis. What happens to this initialization if the voltage is far from the nominal voltage? If the voltage is far from the nominal voltage, so if it's 0.4 PU, for example.
Okay, so actually, if we go to the 12th presentation, we can even. Oh, okay, I don't need the visual then. Yeah, our method rely on the accuracy of voltage magnitude measurements, so probably it's gonna give you less useful initial guesses for the angles. That's okay, we got it.
Thank you. Any further questions from the in-person audience? Yes.
This is Bing from RIT. I have a quick question about the H matrix. So can you explain more why it is positive definite?
Okay, so actually, if we go to the reformulation slide, I can explain it better. That should be the 15th slide. Can we go there? No, next one. Next. No, you are going back. You should go next. Next. Yeah, they are going back and forth. Oh, okay. I will try to explain it without using the slide. So in our reformulation, we use the so you have let's suppose you have a vector for the measurements of power measurements that are injected to a bus, and on the let's say you have other vector S that is for the measurement functions of these power injections, right? And they are complex, by the way. In our reformulation, we use the difference norm of the difference between these two things, and then so because in state estimation you actually optimize over the square of this norm.
Okay.
Once I'm gonna get once I do the norm of these things, I'm gonna get something like C times X, a vector X and norm of this. So because in state estimation you optimize over the square of this thing, if I take the square of that thing, then I'm gonna have C conjugate C.
Okay.
So that's why that
becomes,
and then that's gonna be equal to H.
Okay, so it becomes non-negative because you take the square.
Yeah, and the reason why it's positive definite but not positive semi-definite is because I mean you're gonna need enough measurements so that your system will be observable, and you have to have that in state estimation.
Yes, actually you answered my follow-up question. Then why is not semi-definite? Okay.
Yeah.
Any further questions from in-person audience? Do we have any virtual questions? None. Okay. All right. Well, thank you again, Ivan.
Thank you.
We'll now welcome our last presenter for this session. That is Andres Ramirez from Lehigh University. He'll be presenting ABSCoRES, applying credit scoring methodologies for risk estimation in energy assets and grid management. Andres, please.
Thank you. I just want to make sure that my audio is connected. Can you confirm if you can hear me, please?
Yes, you sound good.
Perfect. So thank you. My name is Andres Ramirez. I'm a research associate with Lehigh University. I'm here with Professor Alberto Madrid today, and I'm going to speak about our project, which is application of banking, scoring, and rating to electricity systems, or better known as ABSCoRES. And we go to the next
Andres,
slide,
if you could elevate your volume a little bit, that would help. It's very quiet in here.
Yes, absolutely. I'll try to speak up.
Okay, thank you.
So if we can go to the next slide, please. So the theme of this project is composed in several components. So from Argonne and Lawrence Livermore National Laboratories, we get our forecasts for renewable energy sources and load or demand. And from the MIT, we get all our security constraint economic dispatch and security constraint in commitment optimization models that we use as input, and that I will explain later on how they integrate into our methodology. And from the Lehigh team, we are in charge, and this is mostly what this presentation is going to be, around the generation of the risk scores and the scoring methodology we apply. Can we go to the next slide, please? So the ABSCoRES Risk Project is an initiative to create a risk scoring system for energy generators, prosumers, and other stakeholders in order to quantify the likelihood of imbalances due to the inclusion or accelerated inclusion of renewable energy sources. The main goal of the project is to quantify, again, this risk measurement, and we understand risk as positive or negative deviations from the unit commitment. These deviations are estimated or are quantified as risky after they surpass a specific threshold, and this threshold is estimated from the data. The problem or the opportunity is how can we use the data that we've got, both from the security constraint, unit commitment, and economic dispatch, and also characteristics of the generators, spatial and temporal characteristics, in order to better evaluate and produce a risk assessment in the electricity system. And then how can we incorporate or use that risk assessment in order to improve the efficiency or diminish the overall system risk? And we go to the next slide, please. So we took inspiration from credit scores. You may be aware of credit scores as measuring the probability of default. So the top left chart is similar, or we wanted to put them side by side. A high probability of default in credit scores will likely translate to a low credit score, and vice versa. A low probability of default will equal a high credit score for an individual. Again, I'm talking here on the banking world. What we thought about is how can we use a similar approach and translate that into the electricity system or energy system. So what we decided to do is we need to quantify a measurement of risk. As I mentioned before, this measurement of risk is related to the probability of deviating from the unit commitment. And then how can we translate that risk into a credit score-like measurement that we can provide to all the generators and participants of the network, so they can access not only their information, but information from other generators, and that likely looking towards improving the overall risk management of the system. The top right chart shows an example of what we call a threshold for action. That would be thresholds where risk is high or low, and we could create actions to reoptimize and try to bring down the risk of the overall system. Here we're showing two distributions. So a distribution for high risk equaling a low ABSCoRE, and a distribution for low risk equaling a high ABSCoRE. After certain thresholds, we could set up constraints for the generators in order to minimize the risk of the system. The current issue that we're trying to, or the opportunity that we found, is that there's often imperfect or asymmetric information, and there's missing mechanisms to manage the risk due to these information failures. Thus, introducing an independent risk assessment and an information software that provides access to this risk assessment, we intend to minimize this asymmetry or imperfect information and improve the management of risk of the overall system. Can we go to the next slide? So we are proposing a data-driven electric asset risk bureau that enables financial products for trading, managing assets, and system risk in electricity markets. This risk bureau will use centrally managed and market-driven systems, operational decisions, and long-term planning. And then we'll also be able to assess the impact of day-to-day high-impact, low-probability events. And these we expect to bring benefits about access to more reliable data and better understanding of future risks using the assessment that we have constructed of that probability of deviating from the unit commitment. We expect that less information asymmetry means better dispatch decisions by operators and other market participants. And as I'll show later in the presentation, we've run a couple of counterfactuals in order to assess how the system will change if the risk assessment that we constructed is adopted. Can we go to the next slide, please? So the Electric Asset Risk Bureau that I've mentioned, the goal of this entity will be to develop a novel data-driven probabilistic scoring and rating model, and then to create the information management system for historical data collection and interpretation. So it will serve as an information gathering, processing, and generating for users of the energy grid. And then we seek to, or the goal will be to do the integration of these risk scores into the operational decision making of the user generators particularly, but not only for them in the grid. Also, we seek to identify missing mechanisms and products that using the ABSCoRES could help, again, the improvement of risk management and the access to the information. That is what we're the main goal of the project. Can we go to the next slide, please? So there's 3 steps that we propose for a path for broader adoption of this specific methodology. So the first one would be the buy-in from stakeholders, so obtain support from PGM, CAISO, Excellent, etc. The second stage will be a 2-phase pilot, and I'll talk about this briefly in a second. And then the third step after that pilot and adoption will be the establishment of the independent Electric Asset Risk Bureau. And we go to the next slide, please. So the 2-phase pilot that we propose is first starting with historical information and create a synthetic or digital twin of the pilot partner system to calculate the scores. So this is creating a system that emulates the actual system, and by doing the optimization or the security constraint unit commitment and security constraint economic dispatch and constructing the risk scores, create risk differentiated strategies for each generator at each hour of the day that, based on the information that we've got, will improve the overall risk, reduce the risk of the system ideally. There will be a first phase, which we call centrally planned. And then second phase will be the integration of information from the agents and the interaction amongst them to create a marketplace or a design of market where we could add additional capabilities using not only the information that we're producing and the model that we've got, but also including information from agents and that collaboration aspect that ideally reduces the gap on information or the asymmetry in information. Also, this pilot seeks to identify geographic and sub-regional patterns and characteristics that could help us perform a counterfactual or what-if analysis. Again, everything intended to seek to diminish that asymmetry of information in terms of risk management within the system. The last item I've got here is provide ABSCoRES to stakeholders and market participants. So ideally, this is something that is open and accessible from all the users of the system. And we go to the next slide, please. So the process of onboarding the entities would be divided into 3 steps. That's our proposal. So the first one is the understanding of past data, historical data, that data collection, and understanding requirements of constraints, not only from the system, but also from the generators. Identifying usable data sets and information that can be used and that is that can be integrated into our current modeling efforts. And finally, creating the scenarios, perturbations, high risk, low probability event scenarios that we can test and evaluate in order to prepare for future contingencies. So onboarding entities into the ABSCoRES risk calculation platform, transitional stage, customized for each entity, and then the integration of all these previous steps into a data analytic and visualization platform. I will speak about the score calculation in the following slides. We can go to the next slide, please. Thank you. So this is the methodology pipeline of the risk score ABSCoRES that we are proposing. So I'm going to start with the chart on top. We start from scenarios. These scenarios are for renewable energy sources, solar and wind energy for New York ISO. And we also get scenarios for demand. We are running the model both for 2019, August 2019, as historical data, and then we're all applying this methodology into the future using the proposed 2030 grid. And that's where the forecasting procedure becomes important, because we need not only the demand, but also the generation from renewable sources for that specific grid topology in 2030. These scenarios are used in the simulation of the security constraining commitment and economic dispatch using the optimization modules. And then the output of this optimization module and the data that we can extract from this is used in the estimation and scoring pipeline and module. This scoring pipeline and module consists of 4 key steps. First one is feature engineering, extraction, transformation, and loading. So using the data from the optimization module and adjusting it so it can be consumed by the machine learning pipeline. The second step is transforming the data using something that is commonly used in banking, which is binding the features using weight of evidence and information values. What this does is a transformation of numerical features, continuous features, into categorical features that maximize or help classification models to perform much better. The third stage is using this data and this transformed data into our machine learning training pipeline. So this is a standard training pipeline that uses a machine learning methodology that I'll explain later. And then after we run the machine learning model, we do what we call the scorecard generation, or the transformation of the results of this machine learning model into a scorecard or scoring a number that can be then be communicated and used by users. After the scoring mechanism is done, then we propose a re-optimization, that is threshold policies or other types of policies that leverage this information in order to produce a counterfactual analysis on what may happen if this methodology that we're proposing is introduced into the system. We can go to the next slide, please. So the optimization module, we use a direct current linear model of the network flows. I'm showing here a generalized formulation, but basically we model the discrete decision variables and vector of continuous decision variables, as well as constraints for these types of variables and constraints that guarantee that the system can operate if there are deviations, optimal power flow constraints, among others. We implemented the model using an extension of the Mad Power optimal scheduling tool and implemented it in Python for scalability purposes. This optimization module, and I'm happy to refer to the papers published on the specifics of the optimization model. That's not the scope of this presentation. I'm going to concentrate more on the machine learning side and scoring side. So we can go to the next slide, please. I realize these slides are not the latest, but it's fine. So what you're seeing here is the formulation of what is known as an elastic net for a regression model. And that's why these slides are not updated, but it's fine. We can continue. We don't need to change them. So an elastic net is just a regularization of a linear regression using what is known as lasso ridge penalties. In the model that we use a classification model. So to break it down, we have the input features from the optimization of the security constraint, unit commitment, and economic dispatch, and our response variable is a binary feature, 1 or 0, that represents if an energy generator has deviated or not past certain threshold from their unit commitment. If an energy generator has deviated from the unit commitment, we consider that generator as risky. And if it doesn't, well, we consider that it's not a non-risky or a negative observation. For that, we need to apply what's known as a classification module, and we need a specific formulation for that. The biggest change from this formulation, again, this is for the regression case, is that we will need to apply the sigmoid function and the logarithm to run what is known as a logistic regression. But the formulations could be used interchangeably. We can go to the next slide. After we run the classification module and we produce the probability of being or belonging to the risk category, or for each one of the generators, we run our scoring mechanism. This scoring mechanism uses the coefficients from the logistic regression with L1, L2 regularization or elastic net, and the weight of evidence of each one of the features to produce a score metric between threshold that we've established, which are 350 to 850. So we wanted to create a number that was similar to credit score to leverage that information, that knowledge or broad knowledge and usage, and make it easier for participants of the network to adopt eventually. The key component here again is the coefficient of each one of the features that we're using and that weight of evidence that help us translate the impact of the features that we're using into how these features may impact the risk or lack of risk for each one of the generators in each hour of the day. We can go to the next slide, please. So the Electric Asset Risk Bureau will use this information and these models, and it will be an independent entity. It will embed the ABSCoRES risk scores calculation methodology into their procedures, and it will offer advisory and coordination services as well as software solutions to assign the scores to each one of the assets. And these scores could be used, I've mentioned, energy generators, but also grid operators, ISOs, market participants, market monitors, regulators, evaluators, etc. Again, the goal of the ABSCoRES is to minimize the information asymmetry and to provide access to information about other participants without the need of disclosing private or proprietary information. So similar to what a credit score might do. Go to the next slide, please. So I'm going to show some of preliminary results and to give an idea on how we construct and the output of the models. So this is the generation mix of all the fuel types for the forecasted period, so 2030. And these are some of the results that we've got. So we run the model for a specific week of March 2030 and specific week for August 2030. And these weeks were selected because in 2019, August and March, there's specific weeks with what we call high probability low impact events or periods of high stress of the network. So we decided to use those specific periods of time. And what we wanted to show with this slide is how the forecasting and the optimization models are representing the seasonal conditions and the seasonal changes of the network. So on the left chart, you'll see the generation mix for March. So you can see the increased penetration of wind in the proposed 2030 network. And then in August, conversely, you can see how, for example, natural gas has a higher ramp, higher generation quantity. And this is mostly, we hypothesize, due to increased ramping requirements and increased demand. In March, reduced demand and more stable wind patterns reduced ramping in non-renewable energy sources, for example, natural gas. So what we wanted to show here is that the network that we're using and the generational mix is modeling congestion, it's modeling the topology of the network, and it's also modeling the grid characteristics for 2030. We go to the next slide. So these are some of the snapshots of the results that we pulled from the research paper that we published or that is under publication. So I'm going to walk you through some of these results to give you an idea and an overview of how this risk score looks like. So we've got aggregated measurements, but also we've got a generator level at an hourly rate ABSCoRE. So on the top left chart, you will see the distribution of the ABSCoRE for each hour of the day for a specific day. And you can see that this is a bimodal distribution, mostly concentrated around 600 and 800 ABSCoRE, but there's a left tail around 400. So these will be the generators that have a low ABSCoRE will be generators with high risk. And then I decided to select one random generator out of those generators. And the second chart, the top center chart, shows the breakdown of the ABSCoRE for this generator and the impact of each one of the features for each hour of the day. The chart in the top right is also a breakdown of the same generator that shows the confidence interval of the ABSCoRE throughout the day. And as you can see here, for this wind generator, the ABSCoRE is around 450 to 650 for this particular day of modeling or simulation. In the bottom left chart, we've got the total energy generation for 2030 for this specific day for all generators. And you can see the temporal seasonality that it's represented in the graph. And also you can see how in midday, the uncertainty or variance of this distribution is increased, mostly by the penetration of solar energy and of course, wind energy as well. So this increased penetration of renewable energy sources. The bottom center chart shows the average ABSCoRE for all the scenarios that we tested and all generators for each hour of the day. So you can see that in hours of lower generation, so at the start of the day, and then at the end of the day, the ABSCoREs tend to be slightly smaller, meaning that there's higher risk in the system. And then in periods of like around midday, the risk scores get improved for all generators. So we emphasize that this...
Sorry to interrupt. I just want to give you a 3-minute warning. Just 3 minutes left. Thanks.
Appreciate it. I'll try to move a little bit faster. So the bottom right chart is quite important. So we developed the ABSCoRES desk. This desk has a breakdown of all the input-output features and also the ABSCoRE itself through generators over time, through fuel types, etc. And that's the main tools that we plan to use in order to distribute this ABSCoRE. We can go to the next slide. This is, again, a spatial risk scoring, or the analysis of how we found patterns that represent the stress of the network on specific generators, and the risk score captures these risk patterns across the state of New York and the New York ASO grid. I'm not gonna, for the sake of time, I'll move a little bit faster to the results, so we can go to the next slide. Thank you. So the main goal of the project, as again, is to integrate the ABSCoRE risk calculation into a data analytics and visualization platform that is or could be used by utilities and grid operators, and then potentially integrate the ABSCoRES into the security constraint, unit commitment, and economic dispatch in order to, again, seeking that increased efficiency of the system or reduction of risk. So for onboarding entities, it will be a transitional stage where an entity joins and then is assessed, understanding of the data collection requirements and constraints, both for each participant, but also the overall network and community, identify usable data sets, and finally create the scenarios and perturbations for risk assessment and forecasting. I think that's the next slide is the last slide. So I want to appreciate everybody for their time. I'm happy to answer any questions and open for discussion. Thank you.
Thank you, Andres. Do we have any questions from the in-person audience? So I think I'm wrong. Questions from the in-person audience? Oh. Please introduce yourself.
Hi there, Tom Dotto with the Policy Office here at FERC. Is deviation from your day-ahead schedule always an indication of risk that is attributable to the generator, or are generators just possibly dispatched away from that as part of the real-time market?
Since we run the economic dispatch and real-time market, the deviations absolutely can be represented as, for example, non-renewable energy generators responding to fluctuations of renewable energy generators or demand requirements. So the deviation, we decided to use it as a measurement of efficiency from the unit commitment. So if there's a unit commitment, how efficient is each generator on responding or maintaining that unit commitment in the real market? And then the goal is, again, to measure the efficiency of these generators. So we didn't want to penalize specific fuel types or types of generators. We wanted to concentrate mostly on how they perform both in the day ahead, but also in real time to respond to volatility within the system.
Other questions from the in-person audience? We have an online question. Please go ahead.
Hi, Robert. I'm going to unmute you so you can ask your question. Give me 1 second. All right, go ahead.
Hi, Philippe. Thanks for a very interesting presentation. It's Robert here. How long does it take to do the scoring on a system level, on an RTO ISO level? Maybe I misunderstood. Do you do it continuously, or do you do it once, or how does that actually? Yeah.
Yeah, very important question, Robert. Thank you. So there's 2 big steps. Well, I said 3 big steps. The first one is the forecasting procedure, but that process is not required to run continuously. The second step is the optimization step. So optimizing based on the input data, optimizing the network and getting the results from the unit commitment and economic dispatch. That process, I mean, that's highly optimized, and it takes a couple of hours. And then the scoring mechanism, which is training the models, can take quite a couple of days. However, once the models are trained and the parameters are estimated, then it becomes a matrix multiplication of the coefficients. So scoring a generator could be done, assessed in seconds or minutes.
Yeah. Understood,
depending
but
on how your features.
yeah, okay. So once the model is trained, then it's trained on that data. But if you get a change in that data, you would have to retrain the whole model again. I'm taking, okay, so it's not dynamic in that sense, it's static on the old data.
It's static, however, as we've got it right now, whenever there's new data, we're always checking model drift, data drift, model drift, or changes in updating the model constantly, right? So the model will be constantly running and updating on data.
Okay, thank you so much, Philip. Nice work.
Absolutely,
Thanks.
thank you.
All right, thank you very much. Let's give Philip one more round of applause. All right, thank you, everyone. That concludes this session. Our final session will reconvene here at 12:30. So we'll hope to see you then. Thanks. All right, thank you, everyone. We really appreciate you sticking through the whole conference to get to this last session, which we realize is a long one, and we thank you for your patience and bearing with us. We've gotten some feedback that we should think about shortening the sessions next year, and we will take that to heart. And we think we can do it without having to shorten the number of presentations too much overall. So thank you for that feedback. We will seriously think about ways we can do that next year. Without further ado, I'll kick off the final session of today's conference. And for that final session, I'd like to welcome our first presenter, whose name is Farnaz Safdarian. And she will be presenting virtually. And she will be presenting a fast learning-based unit commitment strategy with AC optimal power flow for large grids with direct inclusion of weather. Farnaz, are you with us?
Yes, hello everybody, and thank you for the introduction. So
do you have a camera you can turn on, or are you going without camera?
Yes, actually my face is injured in an accident, so I prefer not to, I have bruise in my face, so I prefer not to, if possible.
No problem. Sorry to hear about your injury. No problem.
Yeah,
if you could speak just if you could speak just a little bit louder, it's a little bit quiet in here.
Sure. So thank you everyone for joining the last session of the day. This is Farnaz Safdarian, and I'm a senior research engineer at Texas A&M. And this proposal is a collaboration with Dr. Thomas Overby and Dr. Joshua Peoples. And I'm talking about a fast learning-based unit commitment strategy with AC optimal power flow for large grids with direct inclusion of weather. So if you go to the next slide, please. As you all know, unit commitment is mainly focused on determining the on or off status of the generation units. And the goal is to meet the demand and optimizing the whole operation cost and considering the constraints such as the capacities of the generators and transmission constraints and the grid constraints. So it's very important and critical for efficient and reliable power delivery. And usually unit commitment involves adding binary variables and creating a mixed integer programming, which is usually DC, so linear. But for large grids and for fast learning, that would be very challenging to solve the mixed integer linear programming, and it can be very computationally expensive. So if you go to the next slide, please. The main goal is to solve the unit commitment as faster as possible and based on the needs is possible that is required to solve a unit commitment with AC optimal power flow, to also consider reactive power limitations. And that makes the problem non-convex, mixed integer, nonlinear. So that would be NP hard. And especially for larger grids with thousands of buses, that would be very challenging to solve this problem. And even with DC optimal power flow, that is a linear mixed integer programming, that would be very computationally expensive with industry scale grids. And as you all know, the size of the optimization problem grows exponentially with the size of the number of buses and the size of the grid. And a lot of times it is required to solve large optimization problems for large grids, and for market analysis, it could be required to solve unit commitment over longer periods. So that would be very challenging to solve these problems. So I am presenting a strategy to solve this problem as fast as possible with a learning-based strategy, and also considering the weather changes directly to the problem. So if you go to the next slide. So the main goal is to solve the learning-based and make it more computationally feasible for a unit commitment, and being able to consider AC constraints or reactive power constraints, and being able to solve this problem for larger grids. And the main goal is to being able to solve, like make these problems solvable. That can be very challenging and time consuming, and it's possible that the solution time takes more than the time ahead that is required to solve these problems. And there are a lot of challenges for this, and creating the learning-based data is one of the challenges, and considering the direct weather changes in the problem is one of the challenges. And another challenge is that all of the units, as you all know, are completely depending to each other, and depending to the load, and depending to the availability of renewable resources. So we are addressing these challenges, and also is like the number of renewables and the size of the grid is growing all the time. And already, even without the grow in the renewables, the problem is very computationally expensive. And the goal is to include the direct impact of the weather to this problem too. So if you go to the next slide, please. This work is a contingent research, like convergence research, that includes like the electric grid data and load and weather scenarios with AI learning-based strategy. And the goal is to do the mathematic analysis and running the simulations, and then to make a strategy that is implementable to the real grid data. So if you go to the next slide, please. So the first step is to create the training data and validate the data based on the real grid data. And if like real grid data is not available, we use synthetic grid data that is realistic but not real. And we gather the real generator data from EIA 860 forms, and the real weather data from a variety of resources. And we use an AI approach, and we are seeking industry partners to support this work. So we will contact utilities to support this proposal and this work. And the impact would be definitely if like optimizing, reducing the cost, and reducing emissions, so it impacts the overall well-being, and for educational purposes, for research, and for industry. So next slide, please. So the first step is to model the impact of weather to the problem. And the main impact of the weather is on the actual available capacities of the wind turbines and PV cells. So we gather all the weather data, hourly weather data from 1940 to the current time, and the outputs of renewable resources are directly modeled based on the availability of weather resources, based on the types of wind turbines and types of the PV cells. That the detailed data is available on the EIA website. So we gathered all the generation information and the weather information and created the models that we call power flow weather models. And we map the, like, for example, Aero5 is a good resource that includes all the weather data for each 25-degree latitude and longitude. So we map the closest weather station to the renewable generators. And based on the models that we call power flow weather models that are like kind of input-output curves and models that calculates the outputs of renewables, we calculate the actual hourly available capacities of renewables. So the unit commitment of renewable generators is directly based on the availability of resources. Next slide, please. So this slide shows all the generators in the US based on their fuel type by color codes, and the sizes of ovals as based on the capacities of these units. And as I mentioned, like the capacities of thermal units change slightly based on temperature, but the capacities of renewable resources can change significantly based on the availability of resources. And like in this slide, blue shows hydro units, like red shows nuclear units, and black is coal, green is wind turbines, and yellow is solar cells, and shows all the generators in the US in 2023 by fuel type. So if you go to the next slide, please. This is a visualization that shows in different times how the actual available capacities of wind turbines and PV cells can change. So in the left-hand side, there is a time with a higher availability of wind and sun, so less clouds. And in the right-hand side figure, there is a time that the availability of these resources is much lower. It's a noon time, so it's a cloudy day, and the wind is not much available. So this directly impacts the power dispatch and should be considered in the power flow problems directly. And the weather changes quickly over time, so it's best to directly include the weather into the problem. So if you go to the next slide, please. This is another visualization of the availability of renewable resources in the whole US, with all the renewable generators shown with wind in green and solar cells in yellow. And the two upper figures are at noon time, and the lower figure is the time that there is the least availability of renewable resources. In the historical data, it's in 1941, it's in the midnight. So as you can see, the availability of wind and solar is much lower than the upper left figure, that is a time with the highest availability of renewable resources. And you see that there is a big difference at these times, and this should be directly considered in the problem, as I mentioned. So, and the other upper figure in the right-hand side is the noon time with the lowest availability of renewable resources. So next slide, please. So also the load changes over time, and usually in the models, like MMWG grid model data, and most of the models, the peak load is considered. But we need to create load time series in bus level to consider all the load changes over time, and we at least need a year for creating the training data. So we considered the FERC data, FERC 40 load data, and based on the load changes in regions, we normalized the load to mimic like the realistic load changes over a year to create the input data. So in the next slide, please. Here shows the regions, and yes, here shows the load time series over different years based on different regions, and how we normalize the load. This is the normalize the load, and then we scale the load based on these multipliers and create load time series over the year for the input data. So next slide, please. So after the input data is created, we are creating the training data to determine the on-off status of the operation units. And if the just the zeros and ones on-off status of the units from utilities are available, we are using like those for the training our model. And if not, we created a fast strategy to like sort the thermal units based on their cost curves. And as I mentioned, like the only thermal units are considered in this problem because like the commitment of nuclear units is predefined, and the commitment of renewable resources depends on the weather. So for the thermal unit, at each time, based on the load and based on the remaining load that needs to be satisfied from the thermal unit, we sort the units based on the cost curves and make the units to satisfy the load. And we also consider a percentage for the loss and to make sure that the AC power flow will be satisfied. So we create the training data and then considering the losses and the reserve, this will be the input data for our machine learning strategy. So next slide, please. So as I mentioned, the status of all units are dependent to each other in the unit commitment problem. And for that, we propose a multi-label and online, as I will explain more. So the main challenge in using machine learning in electric grid problems is that the electric grid is changing, consistently changing over time. And if like one generator is being added and one transmission line is being added, we don't want to repeat the whole process of the training. So for that, we use an online and physics constraint algorithm that considers, keeps the memory and only considers the changes in the grid and adjusts the grid based on the changes. And for multi-label, that is because like the status of all the units are dependent, and there is like more than one possible status. And it is like, if you go to the next slide. Next slide, yes. So all the if we have n number of generators, there is like 2 because of zeros and ones, and 2 to the number of n possible status of being on and on for all the generators, and all of these depend to each other. So for this, we use a multi-label program, and then we use like we take out the known unit types based on their fuel types, as I mentioned, renewables and nuclear. And then we use a scenario reduction to consider like the reducing the size of the problem. And then the multi-label is different with like a multi-class, because the number of classes in a multi-class classification is unknown, and is not just a binary classification, and is not just a multi-class classification, because like each unit is in an arrow of zeros and ones. And the final arrow is determined based on the probability of the units being on and on, based on or off, based on the historical data. So this multi-label solves the challenge of the unit commitments with all the possible, like to the number of n possible arrays of zeros and ones. And if you go to the next slide, please. So for the challenge of the electric grid being changed all the time, and to avoid to repeat the training part of this strategy, we propose an online learning that is considers any change in a grid as an anomaly, and then consider the optimal power flow constraint just to that change, and updates the data based on any change in the grid. So there is no need to repeat the whole process of learning as the grid changes, because like every day is possible that more renewable generators are being added, or even more thermal natural gas units, combined cycle CHP units are being added. So we don't want to repeat the whole process with like changes on the grid, and we consider all these changes, and just consider the change for the learning-based strategy. So next slide, please. This is the whole strategy in a flowchart. So if we add the input data and we consider the input data as like all the electric grid data and the weather inputs and the capacities of the generators and the cost curves of the generators, and we also consider the minimum on and off time and ramping, like intertemporal constraints and hourly load at each bus. And then we create the input data for machine learning. So as I mentioned, if the utilities have the historical unit commitment, that's the easiest way to consider. But if not, we create an offline strategy to train the data based on the input data, and we just determine the on and off units based on their cost curves. And then we apply the multi-output, semi-supervised, multi-label machine learning strategy for the classification. And then as the status of the units are considered, we will solve AC optimal power flow. And we check in the meantime if there is any change to the grid. We apply the physics constraints and online learning streaming. It's called the lifeline learning strategy that keeps the memory of the previous learning and just considers the changes to the grid and adjusts the learning to the changes. And then we will repeat the process until the status of the units are decided. and then solve the AC optimal power flow, and also consider the accuracy measures for the learning. And if the AC optimal, if we consider the losses and the reserve based on the experience, the AC optimal power flow is solvable and converges. So there's no proof for this, but the initial study shows that it solves the AC optimal power flow on large cases. So next slide, please.
Hey, Farnaz. Oh,
Yes.
okay, you're done. Sorry.
Yeah, if you have any questions, we did the initial study and I can show the results on that. But if you have any questions so far, I would be happy to answer.
Thank you, Farnaz. Any questions from the room?
Hi, excuse me. Hi, this is Derek Wax. Thank you so much. This was really interesting. I see in your appendix that you tried so far random forest canon and MLP. Are there other classifiers that you're going to try, or is there a reason that you are settling on those three first?
We got like reasonable results on these, especially like perceptron-based neural network. And when we considered like multi-layer perceptron, and we created the precision recall curves, the results showed the best classification, like the best precision measurements. So we can like use any method for the classification, but these are the ones that we checked and got reasonable solutions so far for the initial study. And these have shown like good results for usually for the multi-class classification. So we tried this for multi-label classification too, and got good results.
Thank you. Other questions from the room? No virtual questions? Going once, going twice? All right, let's give Farnaz another round.
Thank you.
Thank you, Farnaz. Our next speaker will be here in person, Vladimir Dvorkin from the University of Michigan. Vladimir will be presenting on trustworthy deep learning for electricity market applications. Please.
Thank you. Thank you. Hi, everyone. Thanks all for coming, and thanks a lot for FERC for organizing this workshop. It's a big pleasure to present here in person for the first time. Yes, the title says Trustworthy Deep Learning for Electricity Market Application, but you know how it happens. As I was preparing for the talk, so I will talk about deep learning, but I will also cover some other more recent work of ours. Next slide, please. Yeah, motivation for this work is the fact that we need to decarbonize our power sector, and we have a strict deadline, 2035, which is only 11 years from now. It's a big challenge, and next slide, please. What we know that software will play a very big role in this transition. Next slide, please. Particular mathematical optimization is central to is a very popular software in this area, right? Mathematical optimization, and we've been using this tool since 90s. I think a lot of decisions before optimization came to stage. A lot of decisions were made, say, from a lookup table, so some heuristics, right? And then optimization came to this sector of power systems and changed a lot. We have this wonderful survey of history of optimal power flow formulations prepared and presented at this conference before. And we solve a lot of operational planning problems using mathematical programming. All these abbreviations that you see on the slide is the instances of mathematical programs that are solved by system operators on daily basis, right? And now it's a time for machine learning, right? I think machine learning is exactly the same, have potential as a optimization when it came in 90s. So now machine learning is a sort of a tool that can help us to ease some of the computations that we do in power systems. And particularly it can assist us with a lot of solving a lot of optimization problems in power systems. Next slide, please. And to illustrate this point, let's discuss a typical grid optimization problem that looks like this. So we would have some decisions to be made, such as unit commitment decisions and power reactive power dispatch. We would like to minimize the cost of generator dispatch and the cost of unit commitment, subject to power flow equations, generation flow voltage limits, right? And what is interesting on this picture, I selected some variables and parameters to be appended by theta. What is theta? Theta is a convention for parameter of machine learning model. And by this notation, I want to say that there are a lot of machine learning algorithms that try to assist this problem, right? Next slide, please. For example, Farnaz just was telling us about classification of unit commitment decisions. We can map features into optimal status of generation units and then provide this information as a warm start to unit commitment problem, right, and solve it efficiently. And a similar work was done by Jalal Kazimpur and colleagues at DTU, reference here. Next slide, please. There is also a lot of work being done on predicting net load. It's a classical application for machine learning. So we have variable stochastic renewable energy resources. So we have a lot of sophisticated tools, including deep learning. I will talk about today how we can predict this stochastic process. Next slide, please. There are also more intrusive applications for machine learning, particularly our colleagues from Texas, from University of Texas in Austin, proposed graph neural networks that can map operational condition of power systems directly to real-time electricity price and give guarantee that these prices will found the power balance in the system, right? Next slide, please. Another proposals include direct prediction of generator set points. So, for example, the group of Pascal van Hendrik and Georgia Tech develop so-called optimization proxies that directly map features like vector of loads into active reactive set points of generators. And this is, of course, not exhaustive list of applications of machine learning, but the point is to show that there is one grid, there is one optimization, and a whole population of machine learning models that try to assist it, right? What we know about machine learning, that it's often errors, right? So Farzan told us just now that performance was good. And I think when it's good, it's not perfect, meaning there will always be some errors, maybe rare errors, but they will be there. And also, you see, when we have many errors algorithms, right, they might not really help each other, but instead can be in conflict with each other. Next slide, please. So to this end, in this talk, I want to answer two questions. So the first one is having this optimization and power systems, how we can control the effect of machine learning errors on the decisions that we make, right? And the second question I want to answer is how we can harmonize many machine learning models assisting one grid optimization. Is there equilibrium among them? Next slide, please. And for that, I will overview two works of ours. So one of them is based on deep learning. So and the other one is called Forecast Equilibrium in Electricity Market. Next slide, please. Yeah, and this is based on this first work. Next slide, please. Yeah, here you see the typical optimization problem solved on daily basis, DC optimal power flow problem. The goal is usual to minimize the cost subject to constraints. And this optimization takes as input some parameter from machine learning model. For example, here you see Mace W hat, which is a prediction of a wind power coming from a machine learning model. Then, using the dual variables of these constraints, we can compute locational marginal prices, and it takes this expression on the left. And what we see that locational marginal prices will be nothing but a function of prediction that comes from machine learning model, right? So if it's an error nurse input, it will be error nurse price. Yeah, and what is also interesting is that there are a lot of network effects in power systems. And even if we have a single wind farm, the errors of prediction from one wind farm will propagate to entire grid, right? So we'll have pricing errors across the whole grid. And as evidence, next slide, please. Look at this IEEE 118 bus system. This is the only wind farm installed at on the northern bus there, north and middle. It has some real data. And what we did, what we show on this map is a difference between locational marginal prices on average on the perfect prediction and the prediction given by some machine learning model, well-trained machine learning model. And what we see that majority of the buses, they don't see any difference, but there is congestion in the system. And we see that some buses, like those in dark blue, they systematically receive lower price with respect to ground truth price. And there are other buses that systematically pay more for electricity, right? And network systems are extremely discriminatory. Outcomes in the system for you depends on your position in the grid. But now we bring machine learning into the loop, and we see that the errors of machine learning propagate through this network and amplify this fairness issues. Next slide, please. To recognizing this effect, so we propose a new architecture for deep learning models that can recognize this effects on prices and inform machine learning accordingly. So, but let's start with the typical architecture of deep learning. So the idea is that we have a data set with features and historical realizations of wind power. And we want to map those features into prediction. So here we have an input layer with features. We have a layer of hidden layers with every hidden neuron having a ReLU activation function. And we produce a forecast, right? This maze W. And when we train this neural network using standard ADAM algorithms, our goal is to minimize prediction loss, the difference between ground truth wind power and prediction. Next slide, please. But what we do now, we extend this architecture. It's a new architecture that includes electricity market clearing as a layer in deep learning. So, and what it does, this layer, it takes the prediction, maze W hat, and computes locational marginal prices based on this prediction. And in the loss function, we have additional term that computes the distance between the ground truth electricity price and the one induced on prediction. So now we train this architecture, right, that is informed on outcomes of market clearing problem. And we can satisfy some trade-off between forecast accuracy and the error of pricing that we produce. And this idea, it's not novel. It's been proposed by CMU 2017, but we found this very original application, how we can inform machine learning model on the outcomes of electricity market clearing problem. Next slide, please. Skip 4 slides, please. Next slide. Next slide. Okay, cool. One of the challenges is that it's extremely difficult to optimize this deep neural network architecture because of the presence of optimization problems. So we had to speed up the computation. And what we did, we come from the classic market clearing optimization problem. We found some equivalent primal form, but then we take a dual of this problem. And what we see is that in order to derive prices, map predictions into electricity price, we need to solve this very compact quadratic optimization problem that only has non-negative constraints on dual variables. This structure is very convenient and particularly amenable to fast and proximal ADMM-like algorithms, like Ellison was talking about yesterday. Next slide, please. Let's look at some experimental results of applying this architecture to predicting electricity prices on a range of power system networks. So we use a real-world data set from a real-world wind turbine. We have features like wind speed, wind direction, blade pitch angle, and we compare the two architectures, one with standard deep WP, deep learning model for predicting wind power, and deep WP plus that is informed by market clearing outcomes. Next slide, please. And here is the results. So on the left, you see application of a standard deep learning model. That's something that you saw before. That's how prediction errors propagated in electricity pricing errors. And on the right, you see the outcomes of a price-informed deep learning network. What is interesting is that it's a less of a gradient on the right picture. We see that we tend to uniform the errors across the network. And when we looked below on the range of errors, we see that the first model gives us errors on average between -4 and $1 per megawatt hour, and this is on average. And the right model gives us a symmetric interval of the error, ±$1 per megawatt hour. What it means is that informing deep learning model on electricity market clearing, it recognizes the asymmetric cost of generation and managed to produce such predictions that result in uniform pricing errors across the grid. And this kind of help us with resolving the fairness issues, these discriminatory systems. Next slide, please. Here you can see how bias is introduced to prediction models. We see some parts of this wind power curve that we try to predict, and we see that at some parts of this curve for different wind speeds, the model systematically overpredicts with respect to baseline model. And the idea, these overpredictions, they reduce the quality of forecast, but they significantly reduce the electricity pricing because of asymmetric cost structure. Next slide, please. Here, the table shows you the results for several standard test cases with only one instant wind farm. And we see that the standard architecture produced the minimum prediction error. This column is a prediction error. And our informed model produced larger prediction errors for the wind power output. But next slide, when we looked into electricity pricing errors, we will see that they significantly reduce, and they reduce with the size of the even more as the size of the network increases. Next slide, please. Here, CMR shows you the worst case pricing error, and we see that in some system it can reach as much as, let's say, $37, $31 per megawatt hour. And these errors will all be present because of the erroneous nature of machine learning predictions, but we can significantly reduce them up to 25% with our model. Next slide, please. So in this first part of the talk, we saw how machine learning models affect electricity prices, right? From one single wind farms, but we have a lot of renewables. We have a lot of agents using machine learning model to inform the strategies. So the question is if there is equilibrium among them. Next slide, please. And to answer this question, let's look into standard prediction of problem for wind power. So we have a data set, we have a machine learning model, and we want to learn parameter theta star that will minimize the prediction error across the data set. So what the model outputs and what the ground truth, we want to minimize the distance between them. Next slide. Recent research was showing us that this is suboptimal for wind power producers particularly, and there is a better objectives to be optimized, and we can produce so-called revenue optimal forecast. And the idea is that we can leverage electricity prices and to optimize our parameter theta by computing day-ahead revenues, it's given here on the bottom, and the real-time penalty that is induced due to errors of prediction from the day-ahead market, right? And so we can optimize this parameter theta to maximize the revenue of our forecast. Next slide, please. Having many producers of that sort, we built an equilibrium model that where every wind power producer maximizes the revenue by maximizing the revenue from the real expected revenue from day-ahead and real-time markets, and subtracted by some cost here, which can be prediction loss, right? And we also have this feature selection here given by L1 norm that help us to find the best features that result in the largest revenue. Next slide, please. In this equilibrium problem, we also have conventional power producers that simply take prices as input and compute the optimal dispatch for the day-ahead and real-time markets. And this revenue subtracted by cost give us the profit. Next slide, please. We also have other participants such as energy storage and others. So we don't discriminate. It's possible to include them too. Next slide, please. What couples all these producers is market clearing conditions. We have a day-ahead market clearing, where you see particularly how machine learning model enters with its prediction. And we have a real-time balance, the second equation here, where we see the difference between the actual realization of wind and the input from the machine learning model. Next slide, please. Under standard assumptions, so first we assume that machine learning model is convex in its parameter theta. Second, we assume that we have a lot of samples. We have a lot of training records to train our model efficiently. And last, we assume that, okay, the system operates in a feasible manner, meaning that there exists a machine learning model that can enable feasible operation for markets and power systems. And the formal result to show that such equilibrium actually exists and is unique. Next slide, please. What is this equilibrium? This equilibrium is a so-called regression profile that consists of all the private machine learning parameters from all the agents in the market, right? And the properties of this equilibrium is that it allows for feasible operations of power grids and markets. It maximizes wind power profits, and every wind power producer like to stick to its equilibrium machine learning model, so there is no incentive to deviate. And it also happens to minimize the dispatch cost across the two market floors, the ahead and real-time markets. It's not so obvious, and to come up with this result, we have to compute this equilibrium first and see it in action. Next slide, please. The first approach to computing such equilibrium is to solving a problem that is familiar to many of us in this room. It's an instance of the electricity market clearing problem, with the difference that it's solved on n number of samples, as many samples as you have in a training data set. So here, for example, an objective function, we minimize the social cost of electricity across the ahead and real-time markets. And we also have the small regularization term that shows empirical loss, how much the quality of a prediction, right? Theta is a regression profile that we want to optimize to compute. And we have a standard set of constraints such as the ahead and real-time market constraints. We have a power floor limits. We have constraints on generation, on regulation limits in real time. And also we have a last constraint for equilibrium feature selection. And what you see is that we compute equilibrium solving this problem, but at the same time, we minimize the cost of electricity, right? So meaning that this regression equilibrium minimizes the cost for the system. And this has some, it's an average cost for the system, so it resembles some ideas of stochastic electricity market design, with the difference that computing this equilibrium doesn't require any changes to market design. Next slide, please.
About 3 minutes left.
I have 3 minutes left. Okay, and 7 slides. It's feasible. Yeah, thanks. Primal. Okay, so we can also, the problem of computing equilibrium using centralized optimization is that we need to gather data in one single optimization, which is difficult. So to bypass this obstacle, we have efficient distributed algorithm, like based on the ADMM. Next slide, please. And next slide, please, again. So let's look at some results. So we have a standard 24 reliability test system of IEEE and 6 installed wind farms. We use the similar data we used before. Next slide, please. And these plots here, they show you the predictions for 6 wind farms installed in the system. The black crosses is the real data. The red dots here, it's a prediction that minimizes the prediction loss. All wind farms are given the same data, so they have the same models, right? But the green dots here shows you the equilibrium prediction. What predictions that if they stick to the equilibrium model, and what you see that it's very bad prediction. Some wind farms systematically overpredict wind power with respect to ground truth, and others underpredict. But in fact, it maximizes their revenues. It minimizes the cost for the system. Let's see why. Next slide, please. Yes, these are revenues for all 6 farms that I showed. Oracle solution is something as if we have a perfect forecast, we can never beat it. We also have equilibrium solution that revenues that result when wind power producer sticks to their equilibrium models. And they also have a baseline solution, which is a simple empirical loss minimization problem. And what is interesting is that if wind power producers will stick to their baseline models, there will always be incentive to deviate from the equilibrium model to increase their profit, right? While equilibrium predictions, they might deviate from the forecast optimal, but they maximize the revenues and everyone sticks to those models. Next slide, please. And this is the outcomes for dispatch cost, right? We have solution, Oracle solution, which is perfect prediction. We have baseline solution, which is forecast optimal, and we have equilibrium solution for wind farms. And what we see is that equilibrium solution doesn't good as well as Oracle, but it's always better than a baseline solution. It holds on average. It also holds at worst case in a 10% of scenarios. We can save a lot for the system when we stick to the equilibrium forecast models. Next slide, please. To conclude, I present you two problems today. The first one, the problem of erroneous nature of machine learning models. So those errors always propagate to dispatch errors, pricing errors, and eventually cause some fairness issues in network systems. But we proposed new deep learning architectures that include electricity market clearing as a layer in deep learning, and we can inform our deep learning predictions based on the market outcomes and eventually prove the applications to electricity markets. And the second problem is that when we have many independent wind power producers, they have a mutual effects on prices one for another. And they can eventually adversarially affect grid optimization, and we can sync them, right? We can sync them by computing so-called machine learning equilibrium is applicable to electricity market. And this equilibrium not only maximizes the private welfare revenues, but it also helps the system to minimize the social cost of electricity. Thank you everyone for attention. I'm happy to take a few questions.
Thank you, Vladimir. Any questions from the room?
This is Guzel from Argonne National Lab. So very good presentation. So my question for your second study. So basically it is a market participation strategy. So the wind farm, so not only try to forecast its wind power, but also determine how to bid into the market to maximize its profit.
That's correct. And as the result showed, for depending your location on the grid, you should systematically over-predict for day-ahead market or under-predict for day-ahead market.
Okay.
And when you coordinate with all other producers in the system, you will end up in maximum revenue, and at the same time, you will help the system to minimize the cost of electricity.
So in this case, whether this it will save the operational cost, that depends on the whole market player.
It depends on the network. It depends on topology, parameters, generation cost in the system. So it's hard to say a priori whether it's better for you.
Worse than the case with baseline.
Yeah, but you basically have to coordinate with others to figure it out what is optimal for you.
Okay, and then for your first study, so you take the AMP different error as basically as the training objective.
That's correct.
So wind power producer does not have a motivation to do that, right?
Oh,
but
yeah.
the system operator would have.
Yeah, that was from perspective of system operator, as if he has a power over some renewable installations there, and it decides how to dispatch them, right?
Yeah.
But so there is no, that was from system perspective. So there is only incentive is to help the system or minimize the pricing error, right?
Yeah. Okay.
Then you kind of send off a long-term signal if someone decides to install facility in your interconnection or others. So maybe you want to do it in the one that kind of maintains a better LMP for you, right? So this is incentive for system operators to do it, and also resolve discrimination of the network system. But yeah, for private incentive is the second part of the talk.
Okay, great. Thank you.
Thank you.
Yujie from ISO New England. I have two questions. First one is clarifying. So when you said the forecast error improvement is larger for a larger network, in those simulations, are they just still having one wind generators, or they have more? Oh.
Yes, it was one wind generator, but it wasn't forecast error, it was a pricing error. So the idea is that the bigger the network, the more LMPs you have, like the larger the vector is. So, and then the more value of this approach for larger networks. So you can minimize the pricing error more for larger systems, and we could see it.
I guess the part I don't understand is I will assume a larger network will be more tolerating to wind forecast error.
That's true. Okay, then we need to speak normalized pricing error. So maybe that would be a better indicator, indeed. But there is still network effects, right? Our results show that it's a one wind farm. So, and in congested network, the effect of the error predicting power from this farm will be propagated to all LMPs in the network. So yeah, I'm not sure about like this effects that you're saying. I think I need to look at it.
Okay.
But yeah, I would think that bigger system should forgive more errors from one. I agree, but
Okay, thank you. My second question is in the second problem in your presentation, you use machine learning to improve the LMP prediction. Have you tried to use that as an input to improve the, for example, storage bidding strategy?
oh no, I didn't think about it. So I was mindful of storage, so meaning that it can be represented in this equilibrium, as well as a wind power producer. So I believe, but I didn't think too long about it, honestly.
Because I think for a small battery, assuming they won't affect the LMP's better forecast will definitely help them to achieve better
That's true.
revenue.
That's true. But yeah, that I can only agree to that. Yeah.
All right, thank you.
Do we have any online questions? No. Any more questions from the room? In person? Going once, going twice? All right. Let's give Vladimir an answer.
Thank you.
Right. I'll welcome our next presenter who will be virtual. It'll be Philip Court from EcoSuite. Philip, I see you're with us. Thank you. He'll be presenting on leveraging underutilized DER edge compute to improve market efficiencies. Philip, take it away.
Great, thanks. Hi, everybody. Yeah, as spoken, so our presentation here is going to be more focused on computing infrastructure and tools to enable machine learning. Next slide, please. And just reminding which topic we're here for. Next slide, please. So a little bit of history on what we're about to... Sorry, can you go back one? Yeah, a little bit of history on what we're about to talk to here. So in 2022, did a talk on dynamic hosting capacity. So this is the ability for DERs to be deployed in greater volume than currently is the norm. And the reference example was what's happening in Hawaii with HECO. And so, anyway, just reference that if you're looking at the slides. It's worth knowing that as a context. Next slide, please. Yeah, so the nature of the opportunity is, as I think pretty much everyone is talking about today, is, better forecasts will lead to more predictable, reliable DER, and ultimately more reliable and predictable DER will generate better grid services and hence increased market efficiencies. Next slide, please. Great. So the presentation today will just spend a little bit of time looking at market efficiencies. Then we'll talk about firm power and the fact that DERs can step into providing firm power, and the opportunity for that is very tangible. We'll then talk about what I term useful flexibility, which is the combination of grid services and forecasts. And then the meat of the presentation is an open source software infrastructure we call SolarQuant, and it's a framework and a set of tools for machine learning experts to improving algorithms and delivering more reliable forecasts. Next slide, please. Next slide. Yeah, so just as a bit of fun, I thought I'd check in with the LLMs, in this case using Gemini. There's the question at the top there, just asking what it thinks market efficiencies are. And we've got enhanced forecasting algorithms, so not a surprise, right? That's what most people are talking about. And then the second point that I've collected there is real-time pricing signals. And that's that's one example of what I would term an energy services interface type behavior, which is the ability for the system operator to influence behavior of DERs, whether that be generation, consumption, or storage. Next slide, please. And the really interesting point, final point from Gemini was it recommended to attend the FERC conference. So well done for everyone who's here. Next slide, please. Next slide. Yeah, so a little bit of background. Right now today in the DER industry, whether it be solar or wind, there's generally hosting capacity constraints for building new projects. So DERs and the project development tends to be grown at the margin of conventional generation. And solar and wind generally run to the max that weather will permit. The sun shines, the solar generates, the wind blows, the wind turbines generate. And there's often limited provision or effort or even interest in offering grid services from these DERs. And DERs are often perceived as a problem that needs to be mitigated on the grid. Next slide, please. So the future dynamic hosting capacity evolved. So this is going beyond what they're doing in Hawaii at HECO, and looking to leverage storage, flexible loads, and also curtailing DERs. So the concept that you could curtail a solar array, in the midday peak, and you can overbuild DERs as well. So just put more solar on than what the grid can handle, and rely on that curtailment to make that okay. And if you balance that with energy storage and curtailment, and load reductions, as you can see in the graph there, there's an optimal point where, if you see the line that's drawn there, the amount of storage being deployed is actually quite small. And you get firm power as a consequence of this optimization. So this is a paper by the reference at the bottom there, Mark Perez and co. They're doing a lot of work in this space. Definitely worth looking at if you're not familiar with this work. Again, DER can provide firm power, and this is the research that's going on there. Next slide, please. So this is a stepping stone into that situation. So again, the definition of useful flexibility I'm terming as grid services plus forecasts. Next slide, please. And so useful flexibility, grid services are, abstract knobs and dials that deliver supply and demand flexibility. Conceptually defined by energy services interface concept. There's some links down below there, and open ADR and real-time price signals are examples of energy services interfaces at play. But the work that's been done there is to define quite precisely the types of energy services interfaces that can exist, and helping the industry move into that future. And then obviously forecasts, real-time and forward-looking situational knowledge that allows those energy services interfaces to be used optimally by the system operator. Next slide, please. Cool. So the key point of what I'm talking about here today is leveraging these and using existing hardware and open source software to achieve these forward-looking forecasts to give us the situational knowledge. Next slide, please. Okay, so Solar Quant, as I mentioned before, is the tool suite that we use to help deliver this flexibility. It's fully open source software available on GitHub. But next slide, please. So SolarQuant is a distributed framework for accelerating machine learning, AI, and forecasting capabilities for the industry. So it not only does it give us access to the data sets that are needed for training, but it's a framework for deploying trained models to the grid edge, and for the outputs of those models to be captured for future training or future refinements as well. Next slide, please. Next slide, please. Yeah, so zooming into what this framework actually is. Obviously a lot going on here, but if you next slide, please, we'll focus in on SQC there, which is Solar Quant Command. It's a environment for data scientists to access, to explore data sets that are available out there. So it's agnostic to where the data might be coming from. And it's also, it's not prescriptive in terms of what tools the data scientists might be wanting to use. So, whether they're using, Python or TensorFlow or whatever, that you can use whatever tools you want. And the access to the data that's available there currently is extremely rich. So sort of 1 minute, 3 minute, 5 minute sort of sample times, data sets from inverters, energy meters, pyranometers, weather data, really rich data sets coming out of that. And then obviously with those data sets, what sort of models you build, what sort of training you might do, that's up to you as a data scientist. So, and that environment is actually, runs inside Docker. So that's, one of the mechanisms via which, it's non-prescriptive. Next slide, please. So once you have your trained models and you're ready to, deploy those models to the grid edge. So what's being highlighted here is actually the compute infrastructure on the grid edge. And, again, from inference perspective, the amount of compute you need here is nothing like what you need for the training. So it's, relatively modest computing infrastructure. Can run those models in this environment. You have access to the real-time data coming from inverters, energy meters, all the devices that might be present on a grid edge project. And not only is that data being captured for future training, but it's also now capturing the outputs from these models. And so you can capture it in the same frequency, every minute, every 5 minutes, whatever you choose to configure this, what we call a grid edge node as. So the output from the model just becomes another data stream. Next slide, please. And the end point for these data streams is cloud infrastructure, and this is like a historian, data lake, whatever you want to call it. And again, this is the data set that future machine learning and refinements can be done on. Next slide, please. Oh, can you go back one? Oh, okay. This is a slightly older deck. That's okay. So really what I was going to show, if you just go back one, because I haven't. Yeah. So you see the GitHub icon top right. Ultimately, what we've got here is is a circle of flow here. You can see it with the arrows. And the trained models are published to GitHub, and the grid edge compute nodes can choose which models they want to deploy and pull them down, right? So, ultimately what we've got there is like a model zoo, all sorts of research being done and all sorts of models being created and trained and published on GitHub, and, people building and deploying their DER projects can discuss and choose which models they want to deploy to give, the outputs that they desire. Next slide, please. So a couple of applications, just to show some examples. Next slide, please. So we're going to just show some examples of preemptive failure detection. That's some ongoing work. and some traditional more performance forecasts as well. Next slide, please. Yeah, so preemptive failures detection is a really important thing in the DER industry. So you've got, O&M and asset management teams trying to, increase the uptime of the DERs. And if you can get some preemptive knowledge that a device is going to fail, that just makes your O&M truck rolls more efficient, and also it means your downtime is going to be less. Next slide, please. So this is some early output with a project that's underway at the moment with Stony Brook University and P&L and EKG Energy. And this is just one example of preemptive failure that we are seeing. And this is using solar quant infrastructure to do this work. And what we've got here, so time along the x-axis is traditional, and signal strength on the y-axis. So we've got effectively 4 what I would call S-curves here, right? And basically when you hit 1, you've got a really strong signal that a failure is coming. And I would argue that anything over sort of 0.4 on the signal, maybe even 0.3, is a very definitive indication that a failure is coming. The orange dots in the top right are actually physical definitive failures that have occurred. And just from a time frame perspective, these aren't days or weeks. This is actually measured within hours. So these are all within 1 day. So not overly useful, but we definitely have other models that are producing similar signals, not quite as strong as these examples, that are longer term in terms of their predictions. But this is just showing that failure prediction is real, and these results in the full publication of the approaches being used are about 12 months away at this point. Next slide, please. Yeah, and obviously, knowing that failures are going to occur in your DER devices actually, ultimately leads to better forecasting as well. Because if you didn't know the failure was going to occur, you would be, forecasting higher production, right? So these are, critical in terms of improving forecasts. Next slide, please. And of course, some traditional forecasting examples, which I'll just flip through quickly. Everyone's familiar with these, but next slide, please. So consumption forecasting, forecasting consumption on site. So next slide, please. Just showing, predicted versus actual, and how they're very similar. Next slide, please. And generation forecasting, for this is from a solar array. Next slide, please. Again, predicted versus actual, not too bad. Next slide, please. And obviously, the whole point of the solar quant infrastructure and what we're talking about here is that forecasting can only get better with better input data. And I think, more grid edge forecasting in real time, that's what this is all about. It means that these data streams, the DERs that are deployed are generating these data streams themselves. So it just creates a richer data set, more data for better and more improved models. And ultimately, better forecasting is going to lead to better grid services and increased market efficiencies. Next slide, please. Yeah, so a lot of words here. This is, I think, really kind of getting into the meat of what we're doing here with solar quant and the open source compute infrastructure that we're using. So we have multi-purpose interoperable edge compute. So it doesn't care what hardware it's running on. It's compatible and can talk to any device out there from any manufacturer using any standard. Whether it be, as I said before, an inverter, an EV charger, an energy meter, grid storage, you can collect data from those, and you can deploy these trained models to the grid edge as well and run on these devices. So the inference becomes a data stream as well. Yeah, it's cheap. These, arguably this compute infrastructure already exists, right? There's data acquisition systems, or DAS, on pretty much every DER that's out there. There's no reason why those same physical hardware units can't be running this infrastructure. Next slide, please. And just some examples of what these things look like in the current world. And obviously there's, like Google's TPU, really low cost, small GPUs, etc., coming that you can augment these existing devices with if you want to run, more beefy algorithms. And the great thing about these things being on the grid edge is they're not reliant on the internet to function, right? They're resilient from that perspective. If you've got, this immediate response to local changes, there's really low latency. And, arguably this compute is free because, as I said before, it's already being deployed. These devices already exist at the project. So it's just a matter of deploying the software. The software is open source. It's on GitHub. It's freely available. So I think it's win-win, and it's really what we're talking about here is better tools for better machine learning and better forecasting, right? And it's a potential, complete game changer to step into this approach. It just makes everyone's job easier, right? So that's what this is all about. So yeah, next slide, please. And thank you very much. Pretty much the end of my talk. And if you skip one more slide, thanking some of the collaborators, some of my colleagues, and Mark Perez as well.
Thanks very much, Philip. Any questions from the room?
Hi, Vladimir, Dvorkin, University of Michigan. Thank you for your talk. You were talking about GitHub, right? And storing the models and data on GitHub. And one of the things I was thinking about that in a power distribution especially, but also in the high voltage grids, privacy is a very big thing. So when we connect to distribution grid, right, we trust our data to system operator, but not other external parties that can even just simply store the data, right? Because we don't really know how it will be then eventually treated, right? How safely stored or misused, whatever. So is it part of your considerations, like privacy of the customers and data owners? Yeah.
100%, 100%. So the GitHub is only for the models, right? And, arguably you don't have to publish the models on GitHub if you want. That's just the default for the infrastructure that we're showing here. The actual data, which was, in the diagram is being published up to the top left, that's very mindful of security considerations and, permissions, right? So when you publish that data with this infrastructure, by default, it's private. If you want to share security tokens to someone to access either all of the data you've published or subsets of the data that you've published, that's part of the framework. So you can choose to give them a token that gives them access to one data element from one project, or you can give them a token that gives them access to the entire project's data set or all of your project's data set, right? It's your choice.
And also, you're saying models, right? Models is also a function of data, right? So you can start making inference who was present in the training data set, who is not. So it's a bit risky, right? So,
yeah,
no,
that's right. So, yeah, that's right. It's a slippery slope, right? So you don't have to publish them publicly on GitHub. Obviously, you can have private GitHub repositories as well. So that solves that problem.
Yeah, thank you for commenting on this.
Yeah, thank you. Great question.
By the way, thank you for joining. And, it's really long and really happy to see you. And yeah, so usually in the classroom, this time students are going to sleep, and I hope I kind of catch your attention. Yeah, so great. So hello, everyone. My name is Ruan from MIT. I'm currently a postdoc. And before I go into the technical detail about this talk, I would like to give a really short opening to kind of let you know that why this presentation might be interesting to you. So, for my PhD, I'm working quite a lot of time. I would say spend most of my time to fight against the noise, fight against uncertainty We don't like that. We have renewable, we have solar that's not deterministic, so we don't like it. We always think that noise is kind of a bad thing. It's kind of a troublemaker. But the question I would like to ask today is that, is it always the case? Or is it some situation that noise is what we want, or noise will help us in some cases? So today, this time I will give an example to show that sometimes we need noise. Okay, so let's go. Next slide, yes. So we are going to talk about privacy preserving demand response by synthetic data. So this is a joint work with Mortaza and Orden. Yeah, so we are all from the, so Mortaza is the previous member of our group in MIT. So we are working quite a lot on this power system operation, battery demand response, quite a lot of this stuff. And my work is mostly focused on distributed energy resources. So we will talk about that from the DER perspective first. So next step. Next slide, please. Yes. So we are going to talk about, give a really short background about privacy protection pathway. And then we are going to look into more technical details about diffusion privacy. This is a typical technique to protect the privacy. And then we will use this idea to design a novel demand response solution. And finally, with a short conclusion. Okay, next. Next slide. Yes, good. So, this one, good. So, this is a figure provided by International Energy Agency. So, they just give a long time, focus about what will happen in the future. So they show that what's the flexibility source for advanced economies and also developing economies. So, and then we give the case for 2020 and 2050. So you can see, I just give 2 arrows here. So you can see that in the future, it looks like that at least half of our flexibility will be provided by, other renewable energies, mostly that's distributed renewables, and then batteries and demand response. So if you know more detail here, that the large portion of this kind of resources might be DER or distributed energy resources. Next slide, please. So DER are transforming the operation of power system and stressing the need for novel analysis and decision-making models. And demand response is, or demand side resources is an important category of DERs. Just share an interesting story of mine. So the biggest barrier for me, for my research in MIT, is the AC system for the MIT buildings. Usually, it's too cold, especially in the hot summers. I have the same feeling here in this room, especially when I sit in the first row. And also, I have a suggestion. So, in MIT, we are working quite a lot on the smart building control, trying to make sure the set point, the temperature set point can be flexible, and that's really helpful to save money, to save energy, and so that's kind of a demand response. And also for FERC, I have a suggestion. You can feel free to contact us. We are kind of help to save money and save energy for FERC to build a green and carbon neutral FERC together. Yeah, so that's demand response. We have quite a lot of demand response building and also electric vehicles. So now today we are not going to talk about a specific category of demand response, but we are going to talk about the basic idea about taking as a more broad concept. Okay, next step. Next slide, please. Okay. So demand response resources is always small size, and we think there's a quite large number of that resources. So usually we need an aggregator. So aggregator is an intermediate agent connecting the demand response sources and the electricity market. And the efficiency and the privacy protection performance are largely influenced by how aggregators may interact with the end users. So next, please. And for, let's say, think about the residential user, we have a smart meter, and then we will just give our demand curve to the aggregator. So that's a kind of a basic input for the demand response program. So is this safe for you, or or we only submit the aggregate demand curve, and then is it really kind of safe? The answer is no, because we have some technique called non-intrusive load monitoring, or NILM. So this idea, please go to next page. Yes. So the idea of NILM is that they can detect what type of appliance people are using. And so this kind to show some details of, like, let's say, so if I have your energy, if I can estimate your energy use for the electric vehicle, I can kind of understand when you are leaving your home, when you are in your house. And I can know what time there's no people in your house. Maybe that's a good time, to do some bad thing. So that's not safe. So I would like to say, even you just submit your aggregate demand curve is not safe. So we need some new solution to empower the demand response without this privacy concern. So today we're going to show some possibility. So next, please. And turning back to the privacy production, actually we have two technical pathways. The first one is homomonic encryption. So the idea is that we do some encryption and then we do computing with the encrypted data. We do not need to know what the real data is, but we do the computing on the encrypted data, and that will be exactly the same as what you would do with the real data. But the problem for that is that first, there's just limit possible operation you can do, and also it's really slow and computational intensive. Another really popular pathway is differential privacy. Is also our focus today. That is that's a way to releasing statistical information about data sets while protecting the privacy. The idea is that we will inject some noise into this data, and then to make sure this data will be safe to, you cannot detect which one. So the idea is that we say the differential privacy is preserved if an observer seeing the output cannot tell whether a particular individual's information was used or not. So that's the basic idea. So differential privacy is well fits the aggregation process of demand response, and that's also our focus today. Next slide, please. Yeah, so just sum up, what's the aim of our work? The first, we are going to explore a novel approach to address the privacy concern in the current demand response aggregation, and we'll focus on the interaction between the aggregator and demand response users. We focus on the use of differential privacy technique, and also we focus on the trade-off between privacy and efficiency. We will show more details here. So next, please. Okay, go next. Okay, so just 2 slides talking about some theory about that. I know it's a little bit boring, but yeah, I have to bring it here. So what is epsilon differential privacy? So let's say we have 2 data sets, D1 and D2. They have some distribution on that. So in the figure, we have these 2 distribution. D1 is the green curve, and D2 is the dotted orange curve. So now, if we have the output, so think about the vertical lines, we have output, and then how can we say is safe? That means you cannot tell what this data is from. It's from D1 or D2, you don't know. So that's kind of safe. If you can actually tell this data is from D1, it's not safe. So, and then from this figure, we show that this difference between these 2 distributions is bounded by a function of epsilon. So epsilon is a number you can give. It's kind of input, so you can decide that. But the basic idea of this epsilon differential privacy is that when you have an output, you cannot tell which distribution is this from, and then the difference is bounded by some number. So that's our theoretical guarantee. And next slide, please. And it's not that easy to do that. Usually we will go to the Laplace mechanism. So it's a kind of an easy way to implement differential privacy. The idea is that we add the noise. So here you can see we have fx, and then we add the eta here. So eta is belong to a Laplace function. Laplace function I give below there. But anyway, there's some mathematics. But the idea is that we trying to design the eta here. We add to the original data, and then we can, and the theory show that this mechanism is differentially private. So it's really good. So we do this, use this in demand response. Next slide, please. Okay, so that's the basic idea. Now we have, let's say, user 1 to user n. We have data, and then we go to a differential privacy processor,
and then we output some. Oh, this is the old version of my slide, but that's fine. Okay, so we get some synthetic data. So now this data is what we call data with noise. And then we input this data to the aggregator. We make aggregator make decision based on that. And that's the basic idea. But there's two really important part of this flowchart. The first is that how do you add some noise? So there's a controllable noise. You need to consider how to do that at the first part. And also, next slide, please. Another really interesting part is that how can you make sure the decision of aggregator is robust to this kind of noise? So if we add some noise and then you make a complete different decision, that's not good. So we want to make sure our decision is really robust to this thing. So please go next. So now we are going to see some demand response simulation, and I would like to say it's really preliminary, and yeah, I would like to welcome all the feedbacks and comments after that. So let's go to see what's the detail. Go next, please. Yeah, so we are going to study a typical aggregator serving a group of residential, commercial, and industrial consumers. The aggregator is going to attend the day-ahead market to match the purchase energy with expected energy use. So it's kind of a dealer. You buy energy and then you serve the user. And then the difference, so there might be some difference will be balanced at the higher cost. So the objective is to make sure these two parts are kind of balanced as much as possible. So, and we are consider incentive-based demand response scheme, and when the aggregator is interact with the consumer. Next slide, please. So this is a typical demand response model from one of our previous work. Basically, the idea is really simple. So let's see the objective function first. We are going to maximize the utility function of the aggregator, or you can just say maximize the revenue. So first part is that we buy some energy from the day-ahead market. So here, D8 is short for the day-ahead market. And then we have two terms, the P plus T or P minus T, that's kind of the imbalance. So we are kind of balance this part with some higher cost. And then the last term is what you need to pay to the user if you ask for some demand response service. So that term is that. And for the constraint, I think it's mostly really standard, just some kind of energy balance and the upper and lower bound. And also, only one thing for that is the demand response. How do we design demand response program? So we use the incentive base. Actually, I update this figure in a version for last Friday, but it's not updated here. That's fine. The idea is that so in this figure, the y-axis is the reduced load, and the x-axis is the reward. That means for the user, if you can reduce your load as more, then I will give you a higher rate. So that's the basic idea. It's more like a stepwise. So we will use binary variables to model this kind of feature. Okay, next slide, please. So we, based on that, we're going to add some privacy things here inside. So recall that we are going to use Laplace mechanism. So we add the Laplace term. You can see the second formula. We add the term in the demand response for the user from the user side. Just we make only this change. And then, so now we have a new variable called PDR star, and now we just replace it in the objective function. And we want to show that we want to inject some noise in this demand response variables and see what was the outcome. So we're going to see some simulation next. Okay. Okay, maybe I think I have one slide. So maybe go next. I have one slide to show some detail about how we design. Yes. So in this formula, if you remember for the Laplace term, we have an input. So that's in that formula is S over epsilon. So epsilon is something we already talked about. So S is the kind of sensitive. It should be set as the maximum change of the user response. So this kind of, you can get this or estimate this from the history data. So based on that, we are going to see more details. So we are going to use the CPLEX to solve a MILP problem. And then we want to see if we inject different level of noise, what will happen. So please go next. Good. So first, we just show that we add, I think it's 15% of noise. And what's the curve look like? So here we have so there's three types. There's the residential, industrial, and commercial users. And then all the cross point at some as kind of the data with the noise. Now you can see we only at 15%, so it's not changed too much about the curve, the shape of the curve. And then please go next. Yeah, good. And then we see about the impact. So now we add different level of noise. So you can see, for example, for the first figure, the x-axis is the how much noise you're going to add in this demand response, and the y is the change of the profit. Sorry. Why is not why is the course the induced course? So sorry for the mistake. I also correct that, but anyway, so you can think about y-axis as the difference for the objective function. So okay. So are you going to change the slide, or we just keep on this?
What was the slide number?
Yeah, maybe it's okay. We just go with this slide, and can you go to the previous page? Yeah, it's okay. It's just maybe 3 or 4 slides left. Yes, okay. So so here we just want to say that when you add more noise, the induced course, or you need to the thing is that you add more noise in the demand response actions, then you cannot make optimal decision. That's suboptimal. And we want to show why is the difference between that. So the larger thing means that you are more far from the optimal. Okay. So so that's the thing. So our objective is that 15% is kind of a threshold. Below that, it seems like the difference between the objective function is just manageable. It's our simulation result is kind of 10%. It's not so super hard. But after that, if you inject like 20% of the noise, the change of that will be we just change quite a lot. And also we want to on the right hand side. So this figure want to show some similar thing that we add more noise. We want to calculate the distance between the original point and the point with noise. So it's clear that you add more noise, the distance is larger. So that's something we want to share. Next slide, please. We have already talked about this. So we can see some trade-off between this, kind of simple simulation. That is, you want to protect your privacy, you need to add some noise. But the more noise you add, you will harm your efficiency, or you will harm your benefits. So this kind of the trade-off. You need to make sure what is the point you want to do. So finally, we don't talk about that how to design the optimal noise level that you should input in this thing, but that's kind of something we can talk about. But in this simulation, we truly want to show the trade-off. So that's some trade-off. If you want to protect the privacy, you need to pay something. And here, that is it will have some impact on the profit of the aggregator. And also, we find there's a kind of threshold at 15%. We are not pretty sure if it's true for all other kind of cases. Maybe can you kind of predict this level, and then that would be a good point for us to add the noise. We don't have the theoretical result for that, but we are kind of working on that. Yeah. Okay, maybe go to next slide. I think it's the conclusion. Next, please. Good. So so differential privacy truly provide a reliable and technical sound way for us to protect individual data with additional noise. And then the challenge, I would say the challenge is how to control this noise and how to reformulate the demand response decision adaptive to this noisy input. And here we also point out 2 things we have some really interesting discussion with our colleagues. That first is that how to design a good market mechanism to match this, because for most of the market application, we want the data to be accurate as possible. But now noise is something that you need to add into that. So how do you design some price signal for that? And how do you design some market for that? We don't have the answer. And also synthetic data is is more than just adding noise. So we are also talking about there will be more clever way to generate some synthetic data, like using modern deep learning techniques. So that's all something that we can think about around this framework. Yeah, I think that's all I would like to share today. And it's kind of a preliminary result, and I would like to welcome all the comments and questions. Thank you so much.
Thank you, Grant. Any questions from our in-person audience?
Sayed from Alpha Tracks here. Thank you for the presentation. So one confusion that I had was where you have differential privacy processor. Is that expected to be on the aggregator side or the user end?
We expect maybe a third party, or maybe we can do some distributed decision making from the user side. So our idea is that so that can be different setup, but in this simulation, we assume that it's not from aggregator side. Otherwise, aggregator will not. They know add all the data, and there's no case for them to protect privacy. So maybe it's from the third party or something. Yeah.
Okay, because in the diagram that I saw, it kind of looked like it's on the aggregator side, which defeats the purpose, because they can just access it on the other side of this process. Yeah.
Thank you for the suggestion. Yeah.
Thank you. Any other questions from the in-person audience?
Brief question. Vladimir Dvorkin, University of Michigan. Thank you, Grant. We have also some work on differential privacy, and for some reason I took this notion of privacy for granted and as a starting point. Then as I worked more with this, I was actually thinking, first of all, it's very difficult to explain. Right? It's a difficult concept, right, to comprehend. And actually, the founders of the technology also struggle with this, how you communicate this technology to public. Right, but then when we have all these problems in energy, right, I was thinking maybe there are some simpler definitions of privacy that we can use and convince people to look into them. And as you were starting to work on this, like what was, I don't know, maybe you have some choices, right? What dragged you towards differential privacy, what's not, maybe application specific.
Yeah, I think for this part is more application because we are kind of consider aggregation. So differential privacy is really good for this case. And yeah, there's some different kind of privacy, but from the we are from academia, so theoretically speaking, so that's a really good theory to show there's some bounds and guarantees for that. And for that's a problem for demonstration maybe, but we also talk about that. Like finally, if we have this technique, what should be the product? Finally, we think about maybe there's a box. You just do all the automation for the user. You just input this in your maybe next to your smart meter, and they will do everything for you. But finally, they will give you kind of a monthly report to tell what's happening and what kind of guarantee or what things is happening, what they do, and what you gain, something like that. Maybe there will be a way to let the user understand what's going on here. Thank you.
Thank you.
Any last questions from our in-person audience? Do we have any virtual questions? Thank you. Going once, going twice. All right, let's thank Grant again.
Thank you. Thank you so much.
For our final presentation in this session, I'd like to welcome Adam Christensen, who's from GAMS. He'll be presenting GAMS-Pi, a pipeline-friendly generic algebraic modeling language. Adam, please.
Alrighty. The distinct honor of being the last presentation of the conference. I don't think it's my duty or I'm prepared to summarize the entire conference, but I've got a different perspective, I think, than some of the presenters before. That as a software vendor, we're trying to supply tools and syntax to you guys who are innovating in the electricity market space. And so we want to make that as easy as possible for you. So I'm not necessarily a electricity modeling guy. I have done some of those models in the past, but yeah, we are a software vendor now. So today we just talk a little bit about yeah, pipeline friendly. So pipeline is yeah, admittedly buzzy, but it gets people's attention. So threw it in there. The pipeline part is really just about all the different data sources that you guys are using, trying to bring it into an algebraic model or some sort of framework, do some analysis, and then probably some post-processing and export of all that data so that people can kind of understand what's going on from that model. So the pipeline part, pipeline parts that I've heard to the last couple of days, this is the first time at the conference, so I spent all 3 days to absorb everything I could. I've heard, let's see, weather data is coming in from all sorts of API sources. That's one track. Consumer data, the colleagues at Linux Foundation Energy, they're trying to work on standardizing that process, and that was the first time I had heard of their efforts. I'm excited to learn a little bit more about it as well. Distributed energy resource data, all this stuff, machine learning applications, AI, all of this is stuff that we're thinking about in trying to innovate, kind of self-reflect at GAMS and provide you guys a tool set that would bring all of these things together into one big package. So hopefully that's where we're going. Yeah, because no one I've heard here say that data is going to get easier or that that automation is not important, because those are the two things that are probably not going to happen. So, all right, next slide, please. This is all work with some colleagues mentioned at the bottom, Steve Dirks, Michael Busik, Mohammed Soyturk. Some of those guys are in Germany and obviously couldn't fly out all the way. So just a quick poll. Anybody a GAMS user in the room? All right, like 30%. It's pretty good. So those folks can go off and drink some water for a little bit or something. But for the other people, just real quick introduction. GAMS is an algebraic modeling language. We've been around since the 80s. I think we turned corporate in the 90s. And the syntax is algebraic, just as if you were to write it on a piece of paper. Set-driven algebra. We do all the work of formulating the standard form, pass it off to the solver. Solver does the work of solving. We return the solver will return the solution. We standardize it and then report it back to the user. So one of the key things that we kind of hold core to the GAMS kind of process is that a model can be written completely abstract. There's absolutely no data in this syntax right here, and yet there's still logical consistency between all the set definitions and the declarations of the equations and stuff. Next slide, please. So at the end here in line 12, you could see that we added some new syntax in GAMS 43. We're at GAMS 47 now, so already the slide's a little bit dated, but we can add in all the data, suck it all in, and suddenly the model makes sense in like a numerical way. And the little fire truck and the fire at the top means that happens very fast. So the model gets generated at the solve time, and it goes off to, in this case, it's LP, so it just goes off to CPlex or something like that. But the philosophy here, the GAMS philosophy, is that this tight syntax where a model is checked for logical consistency before any data is added is kind of core to our mission, I guess. So next slide, please. All right, so like I said, GAMS has been around for a little while. So the good parts about GAMS are that it's an algebraic modeling language, easy to understand. Backward compatibility is a core belief of ours as well. This means that when industry or research institutions invest a lot of money in developing a model, they gain some trust in that model. They don't want to suddenly have the rug pulled out from underneath them. They want to have that model kind of live on and be able to run in our new GAMS systems. So that means we have a lot of syntax that has been developed over the years, but it's backward compatible and stable. Active development also means that since 1987, it's also stable. A lot of the bugs have been worked out. It's been highly optimized over those years. familiar syntax, human readable. We have special GAMS data structures that mean that doing the algebra, building the model generation very fast, and that those same GAMS structures enable very, very large models into the hundreds of millions of non-zeros pretty easily. All right, next, please. Okay, the could be better part. This is the self-reflection part. So we're not a general programming language. That's just something that we weren't designed for in the beginning. We don't handle things like paths, OS paths or something. It is not something that we've been specialized in. Even string manipulation is kind of outside of our wheelhouse. But these are very common things to do nowadays. And we would like to be able to offer those to our users as well. So that modern look and feel is something we're missing. The idea that since the 90s, I was still listening to grunge music back in the 90s, so I can't say that I was a GAMS programmer back in the 90s, but I am of a certain age. That the new generation of students coming out from OR schools, systems engineering departments are not necessarily developing in GAMS. They're working in other languages, primarily Python. We hear a lot about that. I'd be curious to talk with other people if they're interested in other languages, but primarily Python is something that a lot of students already have experience with, and they don't want to learn GAMS syntax on top of that. And so we want to get past the learning curve issues of these things. So that was that point. Our GAMS system, if you go out onto our website right now and download it, it's a 2 GB installation, which is just not possible anymore. One of the presenters in this session had a Docker slide up. They use a Docker container to run something. That Docker file probably had a pip installation command in there to pull some stuff down from PyPy, install it into that container, and then they were able to run some Python scripts and stuff like that. You don't want to be downloading a 2 GB file into a Docker container and trying to run stuff. It's just not feasible. So GAMS-Py is something that we're trying to introduce to help solve these problems. All right, integration into pipeline just means that, yeah, we want to be able to modularize GAMS. If you download that 2 GB, you're getting all the solvers, even though your license might not support all the solvers. You're getting all of our utilities. Maybe you don't even use 90% of our utilities. So we've modularized everything. And our relational data-based data structures internally in GAMS are very, very fast, very powerful, but they're not general. So things like lists and dicts are totally common and very, very handy in a lot of cases. So next, please. All right, so GAMS-Py is our new offering. All of this is out there right now. It's not vaporware. You can go and install it right now. It's a Python-based algebraic modeling language based on the GAMS system. So a lot like Pandas and NumPy have compiled extensions in Python. The GAMS-Py has a syntax for algebraic modeling in Python, but leverages the GAMS subsystem as the kind of compiled extension, let's say, and does the heavy lifting. So the performance of GAMS-Py rivals that of regular GAMS, as if you were to just compare the two. All right. Abstract data independent modeling is the same kind of core concept that we had. You can have 0 data models and it would still be it would be checked for logical consistency. Right, it's all pip installable. We took the GAMS subsystem, put it on PyPy, put the GAMS-Py syntax itself. That package is on PyPy as well. So PyPy is the Python package indexing system that you can go download from. In the back end, we're using NumPy and Pandas as the convenient data structures for sparse data storage, and it runs with it runs with our GAMS subsystem. So please, next slide. All right, so I mentioned that GAMS has been a backward compatible system for a long time, which means we've got a lot of syntax that's kind of been developed over the years, useful or not. It exists still because we have a lot of users that have invested a lot of money in developing certain things, and we don't want to pull the rug out from underneath them. GAMS-Py is going to have a little bit more of a Python-like development cycle, we'll be, warning you that we're going to remove something. We don't want bloat. Code bloat is something that we are trying to avoid here. The documentation is already on Read the Docs right now, and we have 100+ models out there that you can go and look at. Some users have even tried, the model library has both the GAMSPy syntax and the old GAM syntax. And so some users have even tried to train ChatGPT to convert your GAMS model into GAMSPy syntax with pretty decent success, actually. All right. To install GAMSPy, just pip install GAMSPy, and it'll pull down all the dependencies that you need. So next slide, please. All right, the syntax looks very similar to, on purpose, to GAM syntax. If you're a pure Python programmer, it's going to look a little bit different, but you can set up all of your set parameter variable objects in the front part of this code. Everything belongs to something called a container. Container is often, it's the container that contains everything. So there's logical links between all of the sets and parameters made through everything that exists in that container. Where things get a little bit non-Pythonic and non-traditional is when we start doing the algebra. So Python is super flexible in that you can overload just about every single operator. You can customize it, and we did in order to mimic GAM syntax, because we felt like we wanted to contain all of that power that GAMS had in algebraic modeling language, and not necessarily fully adopt the kind of object-oriented mindset or object-oriented framework that Python kind of has. So the lines 12 and 13 here, you can see we use the square bracket notation understands the fact that the object I and J are actual GAMSPy objects, and behind them they have pandas data frames, or they could have pandas data frames. And so you still are doing the looping over the set I and J. It's just it just understands the data in the background. So, all right, next slide, please. Models are formulated outside of a container. They understand which container they're pulling from, but it's basically an object unto itself. So this transport model object is something that has a solve attribute. You can put these things embedded inside of other Python for loops, Python data structures, and run them just like anything else. It's just a Python object. You just declare the sense, and you can even stick the objective function directly into the model object itself, and then off you go. All right, next slide, please. All right, here's a quick example of, there's a problem on line 13 where we've indexed over xjj instead of it being defined over xij. And if you go to the next slide, please. If you do this right away, you'll get hopefully a validation error, and it'll say that, whoops, something's wrong. So you hopefully get a helpful message that this is gonna cause problems. So you got to go in and tighten it up a little bit. And again, this kind of mirrors that GAMS philosophy that tight syntax leads to better modeling. All right, next slide, please. All right, I am going to get into the GAMSPy system a little bit more, but just a quick deviation here. We also have Python APIs, and our data APIs are very, very closely aligned with GAMSPy. In fact, GAMSPy inherits the class structure from our data APIs. So you can pass a container that you would create in our data APIs, and then just dump it straight into GAMSPy, and they're completely compatible with each other. So try to smooth out the entire process. So, and the data API is great because you could do things that are not GAMS friendly right now in the GAMS system, because things like looking at, well, the universe of possible data sets out there is much, much larger than the universe of data that is acceptable to GAMS. So you could have dirty data all over the place, and it would be a real pain to clean it all. Hopefully our data APIs will give you the power to do that efficiently, repeatably, and in a pipeline, let's say. So just next slide, please. Yeah.
By the clock, you have about 5 minutes.
Yeah.
left. We know you have a lot of slides.
Yeah, I'm gonna burn through a
So
bunch
feel-
of them.
feel
Yeah,
free,
yeah.
just wanna check
Yep.
your-
Yeah, most of this is, I think the slides are available, right? So most of it,
Yes,
yeah,
yes.
so most of it is resource, yeah. All right, so we can go through all the data cleaning sides of things, but maybe I'll burn through these. So all of this stuff, extra white space, data typing, these are the things that we hope that will smooth out all the headaches for you guys. So next slide, please. All right, maybe one more, please. All right, you might have some random data frame that was generated from a CSV file or something. It has mixed strings, integers, float types, trailing white space. There's a white space after the C. It's hard to see that. And in GAMS, I've started to say that you can't just have clean data. You have to have pristine data that rhymes. But the other thing is that it's true because GAMS GAMS is a sparse data storage system. And if you have a label that is different from another similar label, it means it's two different things. So it has to be exactly the same. And so harmonizing that logical consistency between labels is like paramount to making good models. All right, next slide. So there's a lot of cleaning that goes on internally to try to smooth that out, but we enforce some structure. Yeah, and it's efficient storage. So next slide, please. So UELs, these are methods that are used to kind of modify the labeling of the data. These are super handy if you've got data coming in from all over the place, weather data coming from one API, economic data coming from some other place. My classic example is that you've got one data set labeled with WI for Wisconsin and another data set that's labeled Wisconsin, and you want to make sure that everything is labeled WI because that's your labeling convention. We can go through and do this very easily with some of these UEL methods. So next slide. So you can do any string manipulation you want. You can add these UELs, set UELs, get UELs, rename, remove, reorder. All of this stuff is available. And it's kind of, if you do this in the container before you pass it off into the model, it's like a pause button. You can get all that dirty data resolved and then pass it into the actual model. And it operates at, yeah, dimension, symbol, and container level. So with one line, you can rename every single Wisconsin label to WI, and it's efficient because you're only operating on the unique labels. There's an integer mapping to that the data is stored in, and that is the kind of the power. You don't have to like loop through a million things, a million rows of a data frame. You just have to replace one thing and it changes an entire data frame. All right, next slide, please. All right, next slide, please. The other thing that our data API is good for is converting between different worlds. So there's the dense world of data and sparse world. GAMS is a sparse system, but machine learning models often exist underneath all of the fancy PyTorch or TensorFlow packages. They exist as NumPy arrays. And we want to be able to kind of put dense arrays into a sparse data storage system. So we help you do that as well. So next slide, please. And then same, yeah, so we can go back and forth between dense and sparse. All right, next slide, please. So there's some kind of overloading and kind of, yeah, we're looking at other interactive environments like Jupyter is super popular. We're trying to enable users to not just run up against a bunch of errors because you're kind of running cells out of order or something like that. We've done some magic behind the scenes in order to replace records on the fly and not necessarily destroy all the objects and the linking between all of the objects that exist in the containers. So next slide, please. There's efficient data storage. So yeah, you hear 8760 a lot at conferences like this because that's how many hours there are. But let's just go all the way up to 31,536,000. That's how many seconds there are in a year. So if we had a data frame that was just storing all of that data, yeah, that data frame took up 1.2 gigs on my machine, but after compressing it down into into the pandas categorical data structure system, remapping it into this integer categorical data structure, it goes down to 400 megabytes. So all of this is, supposed to be performant and scalable. All right, next slide, please. Next slide, please. Just go on. Maybe go up a couple more, since I'm running short on time. So the pipeline part of this is that, this is great, is that in one Python script, you can start to bring in data, you can start to clean the data, and then you can also do algebraic modeling. And then if you go one slide farther, there's even some post-processing steps. So in lines, all of the lines in the slides beforehand were kind of the bringing in the data, setting up the sets and algebra. Setting up the sets, variables, and equations. The algebra for this model doesn't matter what the model is at this point, but the algebra is only lines 6 and 7 on this slide. But I didn't leave Python at all. This is all run in one process. I define a model, and then I initialize some variables at the bottom in line 19. And if you go one more slide, yep, all I do is model.solve, and then I can output the log to standard out, and then do some post-processing in order to check some syntax or check some of the records. So if I create a parameter called chk for check, the records are accessible underneath all of this as a pandas data frame if I access the dot records. So, all right, next slide, please. Some advanced topics. We'll just go through these real fast. So next slide. So we can do indexing and slicing, very similar to NumPy indexing and slicing, where you can specify a subset of the elements of a set to like loop over, or just specify ellipses. You can run over all of the indices that you've defined a parameter over. It can be used on right-hand side or left-hand side. All right, next slide. You can have conditionals. So we have a famous $ condition, which is basically an if statement. So in GAMSPy, it's the .where. And it can also be used on left-hand side or the right-hand side. Next slide, please. Yeah, these are just some other kind of details that are probably best left for reference. So next slide, please. Solver options, anything that we interface with can be tuned with solver options, and you can pass all of those options through in a dictionary kind of construct to the actual solve statement, depending on which solver you're working with. All right, next slide, please. Debugging, there are some temporary files that are written to disk in the background. All of that is managed by GAMSPy. If you really want to get at the core of what is happening, you can specify a working directory, and you can access a lot of this stuff exactly like how you would with normal GAMs. All right, next slide, please. All right, we have a newer product called GAMS Engine, and it comes in a few different flavors, but this is our cloud computing platform. So a lot of GAMSPy is helping motivate even some engine applications as well. And GAMSPy and GAMS Engine work well together. You just change the client, and you can say solve on your GAMS Engine instance instead of it being your local machine. Or you can also install GAMS Engine on your own HPC if you're a large company and have such a resource, or a large national lab and have that resource, and you want a job queuing and management system, then GAMS Engine is particularly tuned for solving a bunch of GAMS models, thousands and thousands of them at a time. All right, next slide, please. All right, this is just my wrap up. There's some other advanced things on the back for reference if you want, but GAMSPy is a Python interface to GAMS. You don't have to leave the process in order to do your algebraic modeling. You can do all of your data inputs and data outputs straight from that one script. We're still accessing all of our state-of-the-art optimization solvers. Everything that we support in GAMS is available in GAMSPy. We hope that this is a new way to think about how to move data into an optimization problem and solve problems. And it works a lot with, works well with all of our other tools out there. So Miro is our kind of GUI front end. GAMS Engine is our cloud computing system. NEOS is a system of servers around the country, I think. A lot of them are hosted at University of Wisconsin for solving problems for free. Usually it's an academic kind of resource. And again, most important thing, all installable, pip install GAMSPy. And that's all I have for today. If you go one more slide, I'd be happy to be a contact at GAMS because COVID's over now. We're trying to invite people into the office. So because you guys stuck it out all the way to the end of the conference, you get a personal invitation to the GAMS office. If you want to come in and you've got a problem and you don't see that GAMSPy or GAMS can kind of easily solve your problem, we're there to try to adjust the syntax or add a new feature or something. We're lucky that we've got a kind of quasi-academic environment that we try to are always learning from our users. So thank you.
Thank you very much, Adam. I believe we have a virtual question that maybe we should start with.
Yeah, for the individual who is raising their hand currently, I'm going to allow you to speak to ask your question.
Could you unmute yourself, please, and ask your question? Okay. Failing that, any questions from the room?
Will Frazier, NCORD. Could you talk a little more about how GAMSPy works with or without a GAMS license?
Yeah, so we are going through a kind of paradigm shift to GAMS. So the academics in the audience, if you've got a .edu domain, probably by the end of this summer, we're going to be liberalizing GAMSPy. And so if you have an academic, that means that you'll get access to any number of our solvers, the free open source ones, Skip, some of these others that are out there. We'll also be providing our link solver licenses. So that means if you've got an academic Gurobi license, you can hook up to GAMSPy for free. So that's one thing that will be available pretty soon. I don't have a date yet, so don't hold me too close to this, but it should be by the end of the summer, maybe early fall. If you've got a regular GAMS license and you currently want to try out with GAMSPy, we'll give you a free GAMSPy license. We are trying to make them kind of two distinct products, though. There will be a technically different license for GAMSPy than GAMS, but
thank you.
All the same pricing though for industrial customers. Yeah.
Actually, I have a quick question.
Yeah.
I've heard GAMS. You mentioned GAMS philosophy of tight syntax. I've heard another piece of GAMS philosophy is to, I don't know quite how to put this, but to outsource or let other companies and teams specialize in the things they do, like you mentioned, string manipulation and other functions of computing, whereas GAMS will just handle the algebraic modeling with its unique data type and all that stuff.
Yeah.
And then just build good connections to these other platforms and other tools.
Yep.
It sounds like with GAMSPy, we're going in a different direction and trying to bring some of that into an environment. Can you talk about how, just briefly, like, is that a change in philosophy? Is that jiving with the GAMS culture?
Yeah. So we have before GAMSPy came out, we had something called Python embedded code. So you could actually put in a syntax inside of a GAMS file that would pause execution of the GAMS system, launch a Python interpreter, run some Python code. Yeah, sorry. Yep. Right. So you would spawn this kind of Python interpreter as part of a GAMS process, and then run that. That might be a way to handle paths and string manipulation, all that stuff. But so that was kind of maybe the outsourcing part of the compute process that you were talking about. I don't know that it's necessarily a totally different approach, but we appreciate the fact that GAMS is pretty large as a tool, and modularizing and going through the exercise of creating a tool that is usable in a Python environment. It's more lightweight. You don't get all the solvers at the same time. You just install a solver that you need at that time, one at a time, and kind of add this instead of having a monolithic system. Yeah, we're just seeing some advantages to that, I guess. So we're excited about where it's going to go, but so I don't know, maybe we're just learning.
Excellent.
Yeah.
Any virtual questions? Any in-person questions? One.
So my name is Syed from AlphaTraxia. So the concept of GAMSPy is basically, and correct me if I'm wrong, just summarizing what I understood is basically the underlying architecture could be different, but from the user's perspective, it's the commercialized version of what CVXPy does, right?
Yeah, I think that's probably about
so
right.
you just get a license off the solver, and then there's an abstracted way of modeling your problem, right? Do you know like kind of significant differences? Is it like in terms of ability to model larger problems, or has there been any kind of like comparison done on your end?
So I haven't used that package myself, but there are others out there like Pulp. GrobyPy has their own. The GrobyPy would be kind of a similar product to GAMSPy. You're building a model and then trying to solve it. So, but
GrobyPy would be more like a wrapper for the Groovy versus CVXPy. You can hook it to different solvers you want.
Oh, that's true. Yeah. So right. I haven't used CVXPy, but I suspect that we use the syntax that we did because we push all the model generation and the heavy lifting of that process to the GAMS subsystem. I don't know exactly how CVXPy does it, but I suspect that there's probably a container object of some kind or another, or a model object that's going to accept Python objects like constraint sets and stuff like that. And there might be a list comprehension that is used in order to actually generate which constraints are added to that object. Maybe that list comprehension has some complicated logic in it. But if you're looping at the speed of those list comprehensions, this can be a real bottleneck. And we're going around those kinds of data constructs in order to get really scalable and kind of GAMS-like performance out of the GAMSPy system. So.
All right. Any final questions? Going once, going twice. All right. Well, thank you very much, Adam.
Good.
Okay. Well, believe it or not, we are finally at the end of the conference, and thanks so much, first and foremost, to all of you attendees and presenters for sticking it out this late. We really appreciate so many of you who have come from way out of town to be with us, to share knowledge about power market software. We know it's a very niche topic, and we're glad to host this forum to have people exchange ideas and get inspired and excited about what's happening. So thanks again to everyone who presented, everyone who attended, including our virtual presenters and attendees. And we are open to ideas for how to improve the conference. We already heard a couple that I think were very helpful. So if you have ideas, please feel free to email us. We also run a small, it's not small, it's actually huge, email contact list. So you can get updates about the conference. The official updates about the conference are posted to FERC's eLibrary virtual, which is our official record, and to our conference webpage. But we recognize not everybody is constantly checking eLibrary or the conference webpage. So if you'd like to get on the courtesy contact list where we email people as soon as we issue the notice, et cetera, and so on. Please email me and or one of the team, and we'll get you added. Oh, and sorry, yes. Huge thanks to our audiovisual team back there in the booth, Rob Hicks and Levon Harold from Leona Enterprises, who've done a great job keeping the overall experience running very smoothly in terms of the whole hybrid experience and in the room experience. I'm sure some of you remember what it was like during pandemic when we were using WebEx and so on, and then pre-pandemic when we were in a small room with only an audio broadcast and the slides on a smart board, and oftentimes one or both of those weren't working. So we're light years ahead of where we are. If you're new to the conference, trust me, it used to be a lot worse. So thank you for bearing with us again over the years. Anything else I'm forgetting? That's about it. Okay, well, please, if you have research you'd like to share next year, reach out, submit your proposal, and we'll hope to see you then, and have a safe trip back to wherever you came from. Thanks again.